So starting some of the part of the CCIE Enterprise Infrastructure exam, starting some part is focused on the switching, the traditional switching part that we have. So we are going to skip this for the moment. We will start with the routing section that we have to start today. So the first thing that comes here is the routing concept, where we have to talk about the administrative distance, AD value, VRF, static routing, policy-based routing, VRF-aware routing with all the protocols such as like EIGRP, OSPF, BGP. Then we should know how to perform filtering, route filtering with all these protocols. We should know the concept of route summarization, manual summarization and automatic summarization, both the things. We should know the redistribution between two or more routing protocols. We should know the authentication between the routers in the routing protocol. And fast convergence mechanism or failure detection technique using BFD, bidirectional forwarding detection. So what happens, for example, specifically, let's say if you're talking about protocols such as OSPF. Okay, what happens in the OSPF is that in OSPF we have the timers of 10 seconds and 40 seconds normally, 10 seconds for the hello interval and 40 seconds for the dead interval. So within that time interval, within 40 seconds, for example, if I do not receive any OSPF hello message, I will consider the neighbor as down. So for that we have this. So what I'm going to do now, okay, I'm going to, all right. So specifically, for example, when we are talking about protocols such as OSPF, what happens in OSPF is that, let's say, for example, we have the timers of 10 seconds and 40 seconds. So within 40 seconds, if you do not receive the hello message from the router, the neighborship will go down. But the problem is that these 40 seconds for the convergence is way too much. So we want to have some sort of faster convergence just in case if the link goes down between the router, the OSPF neighborship should break right away. It should not actually wait for 40-second timer to expire. See, if the routers are directly connected, then there is no problem. If this like router 1 and router 2, they are directly connected. If the link goes down on one end physically, the link will go down on the other end as well. But let's say the condition is something like that. There is a router and there is a switch in between, and then there is a router. Then if this link goes down, it will not have any impact on this side. This link will still remain up. So this router will take at least 40 seconds to detect that the neighbor router has gone down, and then after the convergence will happen. So I don't want the router to wait for that long. I don't want this router to wait for that 40 seconds before it decides to break the neighborship or adjacency with the router 1. So what we could have done, we could have set the timers, like we could have fine-tuned the timer OSPF timers as well. Like we could have set the dead interval to like 10 seconds, hello interval to 5 seconds, something like that. But remember, if you fine-tune the timers, let's say you set the timers of OSPF to, let's say, 5 seconds, then OSPF will start sending the hello packets in every 5 seconds, and every hello packet will have some size, some bytes in it. So repeatedly, if you are sending the hello packets in every 5 seconds, it will be way too much overhead on the link. Same thing like if you are running some other protocols such as HSRP, we are running some other protocols such as EIGRP, failure detection might be one issue. So what we can do, we can enable a protocol such as BFD, bidirectional forwarding detection. So once we enable the BFD, both the routers will become BFD neighbor. Once we have used BFD somewhere, then they will become the BFD neighbor. And then I can ask OSPF to keep a track on the BFD. If the BFD neighborship goes down due to some reason, then immediately bring down the OSPF neighborship as well. Do not wait for that 40 seconds to expire. We'll talk about more in more detail about the BFD, bidirectional forwarding detection feature. From the routing concepts point of view, these are the things that you should know. Here, the main thing is that static routing, policy-based routing, VRF-aware routing, and all. Rest of the things you might already know. You might not know. We'll talk about that as well. After these things, we'll talk about EIGRP. Remember that we don't have RIP nowadays in our content. Like this routing information protocol version 1 and version 2 both have been removed from the content, so we will not be talking about RIP routing protocol. We will talk about some fundamental properties of distance vector routing protocol, but we will not talk about RIP routing protocols in detail. We'll directly jump into the EIGRP. We have to cover EIGRP for both IPv4 and IPv6. So we'll talk about EIGRP adjacency concept, like how EIGRP decides to select the best path, general operations, topology table, packet types, stuck inactive, graceful shutdown, load balancing, equal cost load balancing, unequal cost load balancing, additional path support. We'll talk about that. EIGRP named mode, why they decided to create the EIGRP named mode and all. We'll talk about that. the convergence stability. If the best path goes down and we do not have any feasible successor in EIGRP, then how the convergence will happen? If the best path goes down and we have the feasible successor in the EIGRP, then how the convergence will happen? So we'll talk about the optimization, convergence, and scalability of EIGRP. Remember that a few things we do not have in EIGRP as well. For example, nowadays EIGRP is also the protocol that can form the neighbor relationship over on the top of the other protocol, such as for example here we could be running OSPF and I can ask this, I can configure EIGRP here, I can configure EIGRP here, and they can form the EIGRP neighborship, and then we can advertise our subnets from here to here as well. So nowadays, just like BGP, in BGP we have this functionality that we can establish the, the neighbor relationship indirectly over two or more routers. EIGRP is also a protocol now that supports this kind of thing nowadays. So we are, this feature is in EIGRP is called EIGRP over the top. Earlier this was in our content, but nowadays they have decided to remove this. We'll talk a little bit about it, but we will not go through in very detail of this feature of EIGRP called EIGRP over the top. Okay, so once we are done with this EIGRP section, like EIGRP for IPv4, EIGRP for IPv6, we'll move on to the next protocol, which is OSPF. And from our content point of view, this is what you should know regarding OSPF. So how OSPF forms adjacencies, OSPF neighborship, network types, path preference, general operation, generic detailed security mechanism, graceful shutdown. Basically, just normal OSPF version 2 and version 3. Version 3 is for IPv6, version 2 is for IPv4 specifically. So we'll talk about OSPF operations. Main focus in the OSPF is going to be on the LSAs. So we have to cover total 6 LSAs. Like we have to cover LSA 1 to LSA 5, and then we have to cover LSA 7. LSA 6, we no longer use the LSA 6 in OSPF as per Cisco. So we are going to focus on 6 LSAs in total. Then we'll talk about fine tuning the OSPF timer, SPF throttling, LSA throttling, some advanced concept of the OSPF, ISPF, incremental SPF, that's like what we say. So we'll talk about OSPF in very much detail. Once these IGP protocol is done, then we'll talk about EGP protocol, and the only EGP protocol that we should know as per our content is BGP. Remember that we do not have ISIS protocol. Earlier in our content we had this ISIS protocol, but nowadays we do not have the ISIS protocol. We'll talk about ISIS protocol like a little bit when we move on to our software defined access section, SDA section. There we will talk about a little bit about ISIS. We'll talk about LIS. Okay, we'll talk about VXLAN. But till then, we are not going to talk about these protocols like ISIS, LISP, and VXLAN. After the OSPF, we'll directly move on to our EGP protocol, which is BGP, Border Gateway Protocol. And again, we have to cover BGP for IPv4, we have to cover BGP for IPv6. And later on, when we cover like MPLS, multi-protocol level switching, we will focus on VPNs. There we will see BGP for VPN v4, BGP for VPN v6. So we'll talk about that as well. Alright, so from the BGP content point of view, we have to talk about IBGP and EBGP. There are two types of BGP neighborship that we can have. One is like within the same autonomous system, and one is in between different autonomous systems. So we have to focus on both IBGP and EBGP. Also IBGP, like direct neighborship between two routers, indirect neighborship between two routers. So in total, like we have, and again, a direct IBGP neighborship, direct EBGP neighborship, indirect IBGP neighborship, indirect EBGP neighborship, and that too on physical IP and on the loopback IP. BGP is one protocol that can also establish the neighbor relationship on the loopback IP. There is a reason why you would choose to establish the neighborship on the loopback IP. We'll talk about that in very detail, but we have to focus on all the types of BGP neighbor relationship as per our content. We have studied so far that in BGP, everything has to be statically configured, for example, neighbors and everything. But we will also talk about dynamic neighborship, which is just a way of forming the IGRP neighborship dynamically between two or more routers. So BGP is also capable of forming the neighborship dynamically. However, certain configurations are required for the same. So we'll talk about that as well. We'll talk about different timers, states. We'll talk about peer group, peer template, which is if you have like 10 neighbors and you have to configure same things on those 10 neighbors, then you will not want to configure all those things statically one by one for every neighbor. So what we can do, we can group all those neighbors in a logical group called peer group, and we can configure the commands for the same. We'll talk about that in very. So once we are done with the BGP neighbor relationship concept, we'll move on to the path, like BGP best path selection algorithm, which is going to focus on BGP path attributes. Remember, one thing you have to be very clear with, BGP best path selection algorithm is a different thing and path attribute is a different thing. BGP uses path attribute to decide like which path it has to prefer. Like if I have multiple paths to go to a same destination, I can manipulate that the router must take this path or the router must take this path based on those path attributes. But the BGP best path selection algorithm has certain criteria based on which BGP decides to choose one path over the another. We can manipulate that by fine tuning those criteria. Those criteria include path attributes. So BGP path attributes and BGP best path selection algorithm, these are two complete different things. BGP uses path attributes to decide like which path is the best path, and we can manipulate the BGP best path selection process by manipulating those path attributes. Then routing policies, like same thing. How can we manipulate the BGP path attribute to decide which path is going to be preferred path for incoming traffic, which path is going to be the preferred path for outgoing traffic. We'll talk about conditional route advertisement. I want this router to advertise the route only when certain conditions meet. For example, if I have this subnet in my routing table, then I will advertise all the prefixes to my neighbor. Otherwise, I will not do that. So I want the router to advertise the routes when certain conditions meet. That comes under this BGP conditional route advertisement. Similar to that, we have a feature called outbound route filtering. We'll talk about communities. We'll talk about different types of multi-homing scenarios in BGP. We'll talk about AS path manipulation techniques such as local AS, allow AS, remove private AS path prependation, regular expression, route reflector, confederation, aggregation at like AS set command when we use the aggregation command, other features such as multipath, add part support, soft reconfiguration, route refresh and all. So these are the topics that we had to talk about from the BGP point of view. Remember, this is not entire BGP. This is just a part of the BGP that we have to cover as per our CCIE Enterprise Infrastructure curriculum. There could be a lot of other things in BGP as well, which you might study in the service provider track. Similar to that, for example, in OSPF, there might be some things that you will study in the service provider track, but not in the CCIE Enterprise Infrastructure. So we will make sure that whatever is in the content is covered. We'll not talk more than this. We'll not talk less than this. We'll cover the content that we have here. Now, up to this point, up to this section 1.5, all the things you might have heard somewhere, like you might have heard about the EIGRP, you might have seen OSPF being used, you might have seen BGP being used, and like people who are working in the production environment, like the next topics might be familiar as well. But for a lot of people, the topics from here, it is completely new. For example, multicasting. You might have covered multicast earlier, you might not have covered multicast earlier. So multicasting is a way of sending a message to multiple yet specific destinations. Like I have a message that I had to deliver to, let's say, 3 out of 4 candidates. Then how can we do that? We'll talk about that in multicast. So layer 2 multicast, layer 3 multicast, we'll talk about that. The protocol that we use in multicast, IGMP and PIM. These are 2 things that we will talk about. IGMP version 2, version 3, and PIM, protocol independent multicast. We'll talk about that from the multicasting point of view. Then we also have to talk about multicast in IPv6. So when it comes to multicast in IPv6, we have something called MLD, Multicast Listener Discovery Protocol, and we'll talk about PIM-v6. So this topic here, section 1.6, focuses on the multicast, which is just a way of sending a message to multiple yet specific destinations. Okay. So IGMP protocol, group management protocol, that manages how the group members can join or leave the group, and protocol independent multicast, which focuses on routing, such as we have OSPF, EIGRP, BGP to cover the routing for class A, class B, and class C addresses. We have protocol independent multicast to cover the routing for class D addresses. Class D address, which is used for multicasting. So we'll talk about multicast in quite detail in our content. So our starting 30% content is going to cover this much. The starting 30% content is going to cover this much. The starting 30% content will cover this much. Yes, Robert, this entire content will be more than enough for the in-core exam as well. Since in-core exam acts as the written exam for the CCIE Enterprise Infrastructure, this is more than sufficient for that. Also, we have the switching section, which is just normal switching, like that you must have covered in CCNP. It is exactly the same. Like I don't see any difference between the CCNP switching and the CCIE switching, apart from the fact that, for example, we have to talk about MSTP in quite detail. We have to talk about private VLANs and all. But apart from that, this is just the traditional switching section that you must have covered in CCNPs. So we'll talk about the switching section most probably after our routing. So this 30% content is going to focus completely on traditional routing and switching, which is like the traditional switching part and protocols such as EIGRP, OSPF, BGP, and multicast. there are total 6 sections in that. Once we are done with this, we are coming to that part. So once we are done with that, once we are done with section 1, we will go to section number 3, which is transport technology and solution, where we will talk about MPLS, and we'll talk about, basically we will talk about VPNs. We'll talk about like MPLS and like different VPN technologies such as GRE, DM VPN, IPsec. So from the transport technology point of view, we'll talk about like MPLS operations, basic MPLS operations. What is LDP? How we can do the ping and trace in MPLS? What is this label? What is this label stack? Different types of routers, and then we'll talk about MPLS based VPN. Remember, as per our content, our focus is only on layer 3 VPN. MPLS is quite like quite in detail. MPLS is a very big topic. What we have to focus is only on this part. We will not be talking about things such as traffic engineering in MPLS. Earlier we had that in our content, but nowadays we don't have that traffic engineering thing. So we will not be talking about traffic engineering using the protocol RSVP. So we will talk about this thing in MPLS. We'll talk about general MPLS operation. Then we will talk about VPNs based on the MPLS, like layer 3 VPN, how the routing happens between provider and customer. What is this MPBGP, multi-protocol BGP, VPN v4, VPN v6, and how can we leak the routes from one VPN to another VPN. As per our official content, this is what we have to focus on. This is what they will ask in your exam, both like written and in the lab. So from the MPLS section, we have to focus only this much. If it is 15%, I can say this is 7.5% of your transport technologies. And then we have to talk about DM VPN, dynamic multi-point virtual private network, DM VPN. We will talk about GRE before this DM VPN, then we will talk about IPsec, and then we'll talk about GRE with IPsec, DM VPN with IPsec. We'll talk about LAN to LAN IPsec, then we'll talk about GRE with IPsec, then we'll talk about DM VPN with IPsec protection. We have in our content both single hub and dual hub DM VPN. So we'll talk about both single hub and dual hub DM VPN. We'll also talk about IKE version 2. We'll not do the practicals of IKE version 2 because as per our content, we don't have to do that. As per our content, we have to identify the use cases of the Flex VPN IKE version 2 basically. So we'll talk about like where we use the IKE version 2, why we need IKE version 2 and all. We'll talk about all those requirements of IKE version 2. If there is enough time, then we will talk about the configuration as well. But as per our content, we have to focus on DM VPN, troubleshoot, configure and troubleshoot, of course, the DM VPN. And then we are going to talk about the GRE. Yes, policy-based routing is already there. Here in the starting, there was a topic called policy-based routing right here. So yes, we'll be also covering the policy-based. Okay, so this transport technology and solution is going to cover 15% of the entire content. Remember, 30% from the starting, 15% from here. And then we'll talk about infrastructure security and services, where we'll talk about like different device security feature on iOS XE. Means like, for example, control plane policing, iOS AAA, how we can enable the AAA features on iOS. We'll talk about from the network security point of view, we'll talk about variety of switch security features such as VLAN access list, port-based access control list, storm control, DHCP snooping, all these layer 2 security features, switching security features. Then we'll talk about router security features such as IPv6 access list, IPv4 access list, URPF, unicast reverse path forwarding. Then we'll talk about first IPv6 first hop security feature, RA guard, DHCP guard, binding tables and all. Port-based authentication based on 802.1x. So this is the security part. This is the network security part that we have to talk about as per our content. Then we'll talk about device system management, where we will see how we can access the devices like line console, line VTY, SSH, SCP, RESTconf, NetConf, SNMP, syslog, and everything. This is the content focuses on the system management. And then we will talk about the quality of service. Quality of service, end-to-end layer 3 quality of service using modular quality of service CLI. Basically, we have to focus on the CLI part of the quality of service. Okay, so we are not going to use any dedicated tool to push all the quality of service configuration. We will talk about the quality of service from the CLI point of view. And from the quality of service point of view, these are the things that we should know, like what are the different types of cost models, best effort, integrated services, differentiated services. We'll talk about that. Mapping how like we can perform the marking and how those mappings are done, like class of service and then DSCP mapping, classification, N-bar, precedence, DSCP, class of service, policy shaping, condition avoidance, uh, hierarchical quality of service, then sub-rate Ethernet link. From the quality of service point of view, this is the content that we have to talk about. So yes, we do have cost quality of service in our content as well. Again, it is very limited. Like we will not go through, we will have a dedicated book for this. Okay, we will go through as per our content. We'll go through all this and let's see how much content from this we have to cover. Then network services, where we had to talk about first hop redundancy protocols such as HSRP, VRRP, GLBP, NTP, DHCP. They have used DHCP very extensively in our current lab. So we'll talk about DHCP, we'll talk about NAT, basic NAT. However, we had to talk about like VRF aware NAT path as well, and VLAN aware software infrastructure, which is just a way of saying that we are going to enable the NAT on iOS XE devices using some different techniques. So we'll talk about that as well. So under the network services, we will talk about first hop redundancy protocol, HSRP, VRRP, GLBP. We'll talk about NTP, we'll talk about DHCP, and we'll talk about NAT. Then under the optimization, we'll talk about SLA, we'll talk about net flow, flexible net flow, track objects and all. We'll talk about that from the optimization point of view. And from the network operations point of view, how can we capture different types of traffic using the technology such as switch port analyzer, SPAN, RSPAN, ERSPAN. We'll talk about that. Then Cisco iOS XE troubleshooting feature such as packet tracer and conditional debug. This again is 15% of the entire content. So you have to, like for example, out of this 15%, the quality of service is quite a big part. So we'll focus a lot on quality of service. Then we'll talk about these security features like layer 2 security features and DHCP, snooping, dynamic ARP inspection, these, then router security features and all, IPv6 first hop security features. So this is the 15% content where we have to talk about security and services. So 30% from the traditional like routing, switching, 15% from the transport technology, and 15% from the infrastructure security and services. 60% of the entire content completely focuses on the traditional routing and switching. Earlier, this content was in 100%. Now what they have done, the content is same, but they have reduced it to 60%. They have removed a few things, such as they have removed, let me tell you, they have removed RIP version 2. They have removed triple P OE, basically WAN part they have removed completely. Okay, so they have removed a few things, but they have added a few more things as well. For example, dual hub DMVPN was not there in our content earlier, but now they have added the dual hub DMVPN. So this 60% content can be completely done on softwares such as GNS, EU. Okay, we can do everything from the starting routing, switching, transport technology, and then transport technology like covers both MPLS and VPN, and then infrastructure security and service. Next 25% focuses on software defined infrastructure. Next 25% content focuses on software defined infrastructure, where we have to talk about software defined access and we have to talk about software defined WAN. So software defined infrastructure focuses on two things: software defined access and software defined WAN, SD-WAN and SDA. Just to give you a brief idea, SD-WAN is a technology that focuses on managing all the WAN edge devices from a centralized point. Push the policies, do the configuration, do the management from a centralized point using some controllers. Software defined technology introduces a concept of controller from where you can push all the configurations from all the locations on your different sites. So the software defined WAN technology, SD-WAN technology, focuses on managing, configuring, like basically centralized provisioning on all the aspects of the WAN edge devices. All the WAN edge devices that you have in your company infrastructure, they can be managed, provisioned from the centralized point using some controller. That controller is named as vManage. We will talk about that in the SD-WAN technology. So SD-WAN focuses on centralized management and provisioning of all the WAN edge devices. And these are the concepts that you should know from the SD-WAN point of view. We'll talk about them later on. What is this SD-WAN solution? What are different controllers? What are the protocols used in the SD-WAN? How we can apply different configuration templates, policies, and all in the SD-WAN. So this part is this is basically software-defined WAN part. And in the software-defined access part, SDA solution focuses on managing all these devices in your LAN, specifically switches. So they say that you do one thing, you replace all your current, like you replace all your current switches, or you migrate, or you basically upgrade your current switches into the SDA compatible switches. And then you can do what? Then you can manage all those switches from a centralized point as well. So if you want to manage all those LAN switches of your infrastructure from a centralized point, then you can go for this SDA technology, which is going to leverage a controller called DNS Center. So DNAC or DNS Center controller is the centralized controller for SDA, and vManage is the centralized controller for SD-WAN. Nowadays, it is possible that we can basically, we can connect the vManage with the DNS Center appliance, so that DNS Center becomes the centralized point to manage all the LAN and WAN devices. So we'll talk about the interaction between SD-WAN, SDA, and everything. We'll talk about the content from the SD-WAN and SDA point of view. And this is going to cover 25% of the entire content, which takes us to 85% of the entire content. Remaining 15% of the content focuses on network programmability. There is no, see, on the Cisco website, we have a DNS Center appliance, but that you will get only, like, you will get the view level of access. You can only explore variety of options. We have a DNS Center appliance here on premises. So we'll be doing all the labs and everything on the real device. Okay, we have a few like 3850 series switches, and we have some 9300 series Catalyst switches. And we have created an infrastructure based on the same that we can actually manage via DNS Center. So we'll do all the labs on the real devices, real DNS Center, and all the real devices. At the moment, as I'm aware, for the DNS Center, the lab access is not possible at the moment, because that is only on the local machines, like only for the local infrastructure. I think like you had to talk to whoever is in contact with you, like Mr. Saurav or Mr. Sugan, and they will explain you in very detail about the same. If by the end of our content it is possible to give you the remote access for the same, it can be given. But at the moment, I don't think it is possible for the candidates, for the students to get their hands on the DNS Center appliance at the moment. By the end, by the time like we go through the content and we reach out to that like SDA part, it might be possible to give that access. But at the moment, right now, at the moment, it is not possible. We have, like, I have completed one of few batches for the same, a few batches on the same, and none of them actually got the access on the real devices. It is just like you had to grasp the concepts from the DNS Center, and whatever things like we are covering in the class, you have to focus on that. And based on that, if you have any questions, we can discuss. Apart from the DNS Center, you can do everything on the GNS, EU, or even for the SD-WAN part, you will be given the remote access. You will be given the access to the labs on the cloud basis. But for the DNS Center, only and only, you had to compromise on that part at the moment. It might be possible at that moment. It might be possible when we reach out to that particular part of the SDA. It might be possible at that time that we can give you the remote access, just so you can explore different options. But if you just want to explore the option, I can tell you some other ways as well. I can tell you, like, you can explore the Cisco sandbox. That DevNet sandbox is there, where you already have the DNS Center and everything there. You can just schedule a lab there, and you can make the topology. You can explore all the options there. Okay, but you yourself will not be able to perform the SDA lab at the moment. It might be possible when we reach out to that content. At that time, it might be possible. But right now, like the lab access for the SDA to the students, at the moment, it is not. Hands-on knowledge for the SDA is not required to pass the in-core exam, actually. they just ask the basic fundamentals of the SDA, like what is Lisp, what is ISIS, what is VXLAN, what is this control plane node. They ask about different concepts of the SDA. They do not require any, you don't have to do any practicals of the SDA in your NCore exam specifically. So I think like about the DNA part, if you want to get more details about the same, you can contact like Mr. Saurabh or Mr. Sugan, whoever uh, is in contact with you, and they will explain that thing in very detail to you guys. And still, if you guys have any question, you let me know. When we talk about that content, I will show you how you can explore all the options of the DNS Center onto the cloud, onto the Cisco D Cloud. Okay, and how can you use that DevNet sandbox to schedule a lab for the DNS Center, and you can practice on there. At the moment, DNS Center is a hardware only appliance. Okay, so it's not possible to emulate or simulate the DNS Center capabilities. Cisco is working on a software-based DNS Center appliance, which will be ready more like as per them. It will be ready by November. So if they launch a software based image file that can be deployed on the ESXi or VMware environment, it will be easy for us to give you the access. But at the moment, since it is only a hardware based appliance, it is not possible to simulate or emulate the same. Okay, so for the DNS Center only, you have to focus on whatever things we will discuss on the class, and you will actually any question you have, you can have a discussion at that point. And for the lab part, you have to see like how we are doing the lab it might not be possible to give you the access of the DNS Center at the moment at right now, but it might be possible when we cover the content, when we reach out to that DNS Center point, it might be possible by then. And if it is there, you guys will get the app. Okay. Apart from that, apart from the DNS Center, everything you can do on the DNS EU and on the like cloud-based portal. That for the SD-WAN, for example, for the SD-WAN, you can log into the I will tell you dc.mylabs.cloud. This is one cloud-based portal that the company has collaborated with, and you can actually there is a SD-WAN topology there, and you can practice everything regarding the SD-WAN onto that topology. If you have enough resources, I can help you building the SD-WAN lab as well. If you have enough resources, okay, like 8 to 16 gig of RAM, 8 to 16 processors, more than 32 gig of RAM, I can help you build up your own topology onto your machine as well. Okay, but this 25% content is going to focus on software-defined infrastructure. And the last 15% content is going to focus on programmability and automation, like network programmability, network automation, infrastructure automation, and programmability, where we have to talk about different data encoding format, how machine talk to machine. This is what we have to understand here. What are the different types of data formats that are there, like JSON, XML, how we can use the different automation and scripting concepts such as embedded event manager, guest shell. How can we enable the guest shell on the CSR router IOSXE devices and do some automation things on there? Interacting with the vManage API, which will be covered in the SD-WAN section. Interacting with the DNS Center API, which will be covered a little bit in the DNS Center section once we cover the SDA part, and interacting with the Cisco IOSXE API, which is covered on the CSR devices. So this network automation and programming, like infrastructure automation and programming thing, can also be done completely onto the local machine. You do not require any specific hardware or any other device for the same actually. So infrastructure automation and programming is going to cover the next 15% of the content. So 60% traditional, then 40% is completely new. Out of this 40%, 25% is for the software defined infrastructure, and then 15% content is for this network automation and programmability. And it total is going to cover the 100% of our content. This is what we have to cover. This is the amount of content that we have to cover. And as you might have guessed, it will take a long time to cover all this content. Any question in the content point of view, let me know. Anything you need to know, anything that does not make sense from the content point of view, let me know. Otherwise, I will discuss about the labs. I will discuss about the books. I will discuss about a few more things. This is just a general discussion, you know. We have not still started the content. We'll start the content once we are done with all these. Any point that you did not understand in this from this content point of view, let me know. Fine. Yes, in the SD-WAN, almost the entire same content is there. So you should have the knowledge of all these things before you take your NCORE exam. So SD-WAN, automation programming, SDA, all this thing is part of the in fact as like NCORE content as well. Kavita, this has to be discussed with the same account Mr. Sugandh or Mr. Saurabh as well. At the moment, like I said, it is not completely possible. But if it could be possible for 4 hours, 6 hours basis, the access can be given on the local premises. But I think like you can get more information from Mr. Sugandh or Mr. Saurabh regarding this. Anmol will talk about the content just in a moment. We'll talk about the time just in a moment. Yes, Shivam.
Actually, I just want to know like how much time tentative it will take.
Yeah, exactly. Just show you. I will show you one Excel sheet and you will get the better idea how much time it will take for the entire content to cover. I would advise you one thing. If you want to cover this content a little bit early, I would advise you to cover the SDA, SD-WAN and automation part in parallel. Because honestly speaking, for example, this SD-WAN, SDA, automation, it has nothing to do with your traditional routing and switching. If you know basics of routing, if you know basics of switching, you can go for the SDA, you can go for the SD-WAN. For example, in SDA, we have that Lisp, VXLAN, ISIS. These three things are main things in the SDA. For that, you don't require any previous knowledge of the same. If you know OSPF, you know ISIS. If you know, like for example, VLAN, you almost know the VXLAN. The point is that for this part to cover, for this SDA part to cover, or for this SD-WAN part to cover, you don't need very extensive knowledge of routing and switching. So if you know just basic routing and switching, you can cover these contents in parallel. In that way, it will actually more like cover the content a little bit fast. Same, you can go for network automation and programmability in parallel as well. Otherwise, it will take quite a long time to cover the entire content. Yes, Shivam, let me know.
Just want to know like along with the SDA, do we also have something related to ICE?
Yes. In the SDA part, we will talk about ICE a little bit, like Cisco Trust Tech, like in the SDA, the policy plane, the SDA policy plane is based on ICE. So we will talk about general ICE operations. We'll talk about how can we create, for example, users in the ICE, how can we create some policies in the ICE, how can we create the policies regarding the user authentication, device administration. We'll talk about just basic things. We will not go through like in depth of the ICE as per our SDA content. I can ask Mr. Saurabh or Mr. Sugandh to integrate ICE related videos into your course so that you get the knowledge in more detail. But from our content point of view, we will only talk about what is the use of ICE in our SDA, how ICE is being used as the policy plane in our SDA, and just general ICE operations. Will not go through the deployment of ICE in a VMware or all those things. Will not talk about that, honestly. But one thing I can do, I can ask Mr. Sugandh or Mr. Saurabh to integrate the ICE related courses into your content, just to give you the idea what is ICE, what are different components of the ICE. And any more question, anyone? All right. So as far as the timing goes, how long it will take for the entire content to cover? Yes, wireless is not in our content. Wireless is in NCORE specifically. So whoever is preparing for the NCORE exam, they also have to cover 5 chapters of wireless. See, I will tell you one thing. The NCORE actually, NCORE is it acts as the written exam for CCIE, EIE, and CCIE EI wireless actually. So CCIE Enterprise Infrastructure and Enterprise Infrastructure Wireless. This NCORE works as the written exam for both. That's why apart from the traditional things, here you also have to talk about wireless, approximately 4 or 5 chapters of the wireless, which is not that much in detail, that much tough, but we have to talk about those 4 or 5 chapters from the wireless point of view as well. So once we are done with all the CCIE content, whoever is going for NCORE, we can have that discussion as now. From the content point of view, how long it will take? I will share this sheet with you guys, but just to give you the idea, switching part, this is for CCIE Enterprise Infrastructure. The switching part takes approximately 24 classes to cover everything. considering 2 hours a day, it will take approximately 23, 24 classes to cover everything that is in our CCIE switching content. It takes approximately 4 days. So one day, like for today, like we are just discussing the content and everything. So from like 1 to like we'll talk about routing, static routing, Ravel static route, VRF, static routing with VRF and all. Then we'll talk about 5 to 11. We'll talk about EIGRP. Then we'll talk about OSPF. You see here, one LSA, one LSA, one LSA per day. It's like that actually. So it's that much in detail. So approximately from day 12 to day 22, approximately 10 classes will require for OSPF. Then we'll talk about route manipulation techniques like route manipulation filtering techniques. We'll start like 3-4 days it will take for everything to cover from the route manipulation techniques, which is route maps and everything. Then we'll talk about BGP. This is the amount of BGP that we have to cover as per our official content. Then we'll talk about IPv6. We'll talk about IPv6, for example, here. This is the IPv6 part, IPv6 fundamentals, NDP, addressing methods, 6 to 4 communication, DHCP, prefix delegation, static routing, OSPF, EIGRP, BGP for IPv6 and all. So approximately 6 classes for IPv6. Then we will go for VPNs. So from here to here, from 49 to 62, we'll talk about GRE-DM VPN, IKE version 2 and everything. Then we'll talk about MPLS and MPLS-based VPN. So the transport technology will take 49 to 62. Then we'll talk about multicast from 63 to approximately 73. Approximately 10 days, we'll talk about multicast. Then we'll talk about quality of service from 74 to 82. And then we'll talk about some generic concepts like management, security, SNMP and everything at the end. So as you can see, 85, 86 classes in total. If everything goes well, we can reduce it to 75 to 80 classes. 75 to 80 classes for 60% of the content. This is the 60% of the content. This does not include SD-WAN, SDA, network automation and programming. Consider 75 to 80 classes for the same. In this, some classes are 1.5 hours, some classes are 145, some classes are 125. So like that. If I go 2 hours, specifically 145, 150, you can consider 75 to 80 classes for the same. 80 classes, 4 class a week, 2 hours a day for 60% of the entire content. Then we talk about SD-WAN, dedicatedly SD-WAN. It will take approximately 24 to 25 classes for the SD-WAN. This is not your CCIE SD-WAN. This is the entire SD-WAN. If I talk about a specific CCIE SD-WAN, it will take approximately 10 classes maximum to maximum, not more than that. But this is entire SD-WAN, where we have to talk about deployment of the controller in different like AWS, on premises and everything. We have to talk about all the controllers. We have to talk about deployment of the controller. We have to talk about routing and everything. So this is entire SD-WAN, not just your CCIE SD-WAN. Okay, so if I say only your CCIE SD-WAN, it will take approximately 10 classes for the same. And if I talk about just CCIE SDA, it will take approximately 5 to 6 classes for the same. So you can consider if I take total 20 classes for that part as well, it will be like 100 classes in total for 85% of your content. And then 5 to 10 classes it will require for the rest of the automation programming concept. So you can consider a total of 110, 115 classes for the same. Now you can calculate the time accordingly. If everything goes well, I don't think like there is any holiday in between. So if I say 2 hours a day, it will be approximately 100, 110 classes in total that we have to go. Most of the time it will take for the starting 60% of content to cover. That is, if I exclude the switching part for the moment, like from day one, it will be approximately 80 classes for this, 85 classes for this routing section only. 85 classes for this routing section. Plus, if you talk about like 10, 15 classes for SD-WAN, 5-10 classes for the SDA from your CCIE content point of view, not the SD-WAN SDA, and then 20 classes for the switching, because you will cover the switching later on. So it will be in total, it will be 130, 140 classes in total. This is the amount of time that we will take for the entire content to cover. These are the topics that we have to cover, that we will cover in this exact sequence actually. So I will share this Excel sheet with you later on once it is done, once it is finalized, like how many candidates will join. I will share this Excel sheet with everyone, and then you can keep a track on, okay, this topic is done, this topic is done, this topic is done. Yes, it will take approximately, overall, if I talk about, it will take approximately 5 to 6 months to cover this 60% of the content. That's why I said, if you want to complete the content a little bit fast, you can cover SD-WAN, SDA, automation in parallel, so that it does not take that much time. It will take approximately 85 classes, 80 classes at most for this traditional part to cover, and then you can go for the SD-WAN and SDA in parallel. But this is the tentative, this is the content that we have to go through. This is what they expect you to know from the written and lab exam point of view. So it will take, approximately this much amount of time. That depends. The question is that am I going to cover the entire SD-WAN or specific to our CCIE content point of view? That thing actually depends. At the moment, we have to start from the routing section. So we'll talk about this thing specifically at the end of this content. At the end of this content, let's see if a dedicated class for the SD-WAN is there, or we can cover only from your content point of view. Both things can be done based on how I'm instructed from the management side to cover. I can cover based on that. If you want to have the complete understanding, as I am aware from the CCIE content point of view, we cover the entire SD-WAN. As much I know from the CCIE content point of view, we cover the entire SD-WAN. We just do not focus on the CCIE SD-WAN. So it will be entire SD-WAN and entire SDA. It's not like only from the CCIE point of view, as per I know. So as you might have guessed, it will take quite a long time. Yes, Francis, let me know. Yeah. Like classroom training, like you can join any batch that is going on in parallel. You can join that batch. Of course, you will get the recordings and everything. But what I'm saying, that you can join the classes in parallel as well. Okay. If there is, let's say, if there is any batch going on in the weekends or in some other time in weekdays, you can join that batch as well. Some of you guys might have already covered the SD-WAN and SDA part, but if not, then you can, if you want, you can cover it like after our like this traditional part is done. There will definitely be a batch of the SDA and SD-WAN, but otherwise you can cover in parallel as well. Both is as per your requirement. You can cover both. All right. If anyone has like any time limitation, yes, I like I said, like the entire SD-WAN will be covered. That's what I'm aware of as well. Like we do not cover SD-WAN or SDA like from the only CCIE content point of view, because if you go through the CCIE content point of view, there is only, I think, like one chapter for the SDA and one chapter for the SD-WAN. So that does not make any sense. But as I'm aware, as per our content, we'll cover entire thing from the SD-WAN and SDA point of view. I will highly advise you to cover it in parallel. If there is any weekend batch, you can join the weekend batch. It takes approximately 8 to 10 weekends to cover the SD-WAN, and it takes approximately 5 to 10 weekends to cover the SDA. So I would advise you to go through the weekend batches so that you can cover the content in parallel. But same 2 hours a day for the weekend as well. Same thing, 2 hours a day for the weekend. So it takes approximately 10 weekends for the same. Timings differs. Timings might be different. That you have to inquire. But as far as the hours are concerned, it's only 2 hours. It's anyone who has any time limitation that they have to complete the content in this time period, I would highly recommend you to go through the weekend batches or some parallel batches as well. So for example, let's say we are at the M+ point. I will share all these labs with you guys. I will share these labs are on GNS. If you want, you can make these labs on EU software as well. Completely up to you. Okay. So these are all on GNS. So for example, if you had to talk about M+ based VPN, so when we will be discussing about the M+ based VPN, this is the topology that we will be talking about. Let me show you the topology. This is a small topology that we'll be talking about. We will modify this topology on as needed basis. So if I need to add some more routers, I will add more routers. I will remove some routers. But for example, this is the topology that we will talk about in the MPLS based VPN. So we'll configure the MPLS, will configure the MPLS based L3 VPN, L2 VPN, backdoor, OSPF sham link, and everything. We'll talk about everything in this topology. But before going to this topology, of course, we'll talk about basics of the MPLS as well. So once we cover the basic MPLS, then only we will go through that. So this is the basic MPLS topology. And then once we are done with that, then we'll go through that VPN thing. Same thing goes for all the other topologies. Same thing goes for example, like when we talk about BGP, this is the topology that we'll be talking about in BGP. This is a basic topology that we'll talk about BGP. We'll talk about everything like router reflector, configuration, eBGP, iBGP, direct, indirect, next, everything we'll talk about in this topology. Similar to that, we have the topologies for like VPNs, like GRE, DM VPN and everything. So everything like, for example, in Multicast, we have a topic called MSDP. So this is the topology that we'll be considering in the MSDP, Multicast Source Discovery Protocol. We'll talk about that. So these are the topologies. There are approximately 13 topologies apart from switching that we have to cover. This is what we will cover in our lab, in our content. When we go through the content, this is what we will cover actually. I will share all these files with you. And you can practice on all these files on these topologies on the GNS. One official book is released from the Cisco side, that is CCIE Enterprise Infrastructure Foundation, written by Narvik Kucharian. So it's a very good. All right, so let's start. Rest of the people, they will join accordingly. So we were talking about we have to start from the routing. So let's talk about the routing fundamental. What is routing, why we use routing and all those things. Let's talk about that. And then we'll go through we'll start with the static routing part actually. So as you already know that a router maintains all the directly connected network information in the routing table, and a router knows about only and only, by default, the router knows about only and only all the networks that are directly connected to it. A reason behind that is when we go on to the interface such as fast Ethernet 0x0 and we configure the IP address such as 12.1.1.1 and we configure the subnet mask onto that particular interface, that router is automatically going to, it is going to use that IP address and subnet mask to derive the subnet actually. So it will come to know that based on the IP address and subnet mask, it will come to know that this particular interface is part of 12.1.1.0/24 network. So all the destinations within that range must be reachable out of the interface FA 0x0. Just basics. So as soon as we configure the IP address on the router interface, like on FA 0x0, FA 0x1, FA 0x2, as soon as we configure the IP address on the router interface, router is going to get that subnet information from that IP address and subnet mask, and it is going to install that in the routing table. One thing to keep in mind is that the router is not going to maintain indivisible IP address information in the routing table. Instead of that, it is going to maintain the subnet information in the routing table. Just in case if the router maintains indivisible IPs in the routing table, like 12.1.1.1 is reachable out of FA 0x0, 12.1.1.2 is reachable out of FA 0x0, 12.1.1.3 is reachable out of FA 0x0. It will be like too many entries. There. Like if we have to go to those, let's say for example 12.1.1.1 to 12.1.1.2 to 55, all these destinations to 54 exactly, if you do not consider first IP and last IP. So just in case if we have to go to these destinations, the exit interface is same. But if the router keeps maintaining the indivisible IP information in the routing table, the size of the routing table will increase a lot. It will require for the router a lot of resources to maintain those much amount of entries in the routing table. So in short, router is going to maintain directly connected subnet information in the routing table. So just in case if you have to go to any IP address belonging to that particular network, you can exit out of this interface. And since now the router knows that this interface is part of this network, it will not allow you to configure the same subnet on any other interface. Because router's responsibility is to connect two or more different networks. The responsibility of the router is to connect two or more different networks. So if you have configured a particular subnet onto an interface, if one interface is part of one particular subnet, it will just not allow the other interfaces to be part of the same subnet. So that is why, like on router interfaces, we have to assign different subnet information. So in brief, the router is going to maintain all the directly connected subnet information in the routing table. So a router knows how to reach to, for example, 12.1.1.0 network, 13.1.1.0 network, maybe 14.1.1.0 network. Router knows about that. But what if the router has to go to some other destinations? What if the router has to go to the destinations? What if the router has to go to the destinations that are not directly connected to it? So for example, you have connected two routers, like this is router 1, router 2, or more than two routers, for example. So here we have some subnet, here we have some subnet, here we have some subnet. So this is, let's call that subnet A, let's call that subnet B, let's call that subnet C, let's call this subnet as D, let's call that subnet as E. So the point is that router 1 knows about A and D, router 2 knows about D, B and E, router 3 knows about E and C. Router 1 has no idea how to go to this destination, or this destination. So on router 1, we have to somehow give the information that how can you go to that destination, how can you go to that destination, how can you go to that destination. On router 2, we have to somehow give the information like on router number 2, we have to give the information that how can you go to this destination, how can you go to this particular destination, because these are not directly connected to you. On router 3, we have to give the information about this, this and this. So all the indirectly connected routes information, all the indirectly connected network information, the router must know somehow. And that is why we have to perform something called routing. We have to actually tell the router that if you have to go to this destination, this is your exit interface. If you have to go to this destination, this is your exit interface. And based on that exit interface, you can reach out to that particular destination. That information we have to provide the router either statically or dynamically, completely up to us. But whole point is that routers must know, all the routers must know how to reach out to a particular destination so that they can route the packet from one interface to the other interface. So what exactly is IP routing? IP routing basically is a process of forwarding the packets from one network to another network. And for that to happen, for the IP routing process to happen, for the routing to happen, a router is going to consult the routing table. In the routing table, by default, router maintains all the directly connected network information. All the indirectly connected network information either has to be configured by the administrator statically, or it has to be learned via some routing protocols such as link state, distance vector routing protocol, or BGP path vector routing protocol. In short, either the route information can be administered statically by the administrator, otherwise the routers can exchange some messages and learn the routes dynamically, automatically. So in both the cases, we have to provide the router with the information about all the indirectly connected networks. And then only the router will be able to perform the routing properly. Now I have a few questions here. Router 1, same topology. Router 1 has a LAN subnet A, router 2 has a LAN subnet B, and router 3 has a LAN subnet C. In between router 1 and router 2, let's say the subnet is D. On between router 2 and router 3, let's say the subnet is E. When we cover static routing in our CCNA, or when we cover the static routing in our CCNPs, we are generally told that if you are at router 1 must know how to reach to this destination. Router 1 must know how to reach to this destination, and the router 1 must know how to reach to this destination. Otherwise, you will not be able to ping, trace, whatever. Now, my question is, if I'm sitting at PC number 1 and I'm going to ping route like this destination B or this destination C, do I really need to give the information about this subnet onto the router 1? Do I really need to maintain this particular subnet information in my routing table? Or even if I do not maintain this subnet information in my routing table, I will be able to reach out to this destination C that is connected onto the LAN side of router 3. Question is, do we need for example, on router 1, do we need to maintain this subnet information in the routing table to reach out to this LAN destination C or not? Yes or no? Same, if I'm at router 3, do I need to maintain this subnet information? Do I need to maintain this subnet information in my routing table in order to reach out to this destination A? We can configure a default route, but you know that is a whole different thing. So always keep in mind that the routers are going to perform destination-based routing and destination-based routing only. So just in case, for example, you are sitting at this machine and you wanted to ping to this machine and this machine, the only routes that these routers require are to go to like B, C, and A. So actually, we do not need these subnet information. Like we don't need these routers to maintain these subnet information in the routing table in order to route the packet from A to B, from B to C, from C to A, respectively. And when we cover the topics such as OSPF, they will specifically ask us that In my routing table, I don't want to have those transit subnet information. If you are going to do the static routing, since in the static routing, all the configuration is done by the administrator manually. So it's up to the administrator if the administrator is going to give the information about those subnets D and E or not. I would advise that don't do that. And we can only give the route to go to this LAN subnet A, LAN subnet B, and LAN subnet C. We don't actually need any route to go to those transit subnets. We don't actually need a route to go to this subnet. We don't actually need to have a route to reach to this subnet in order to reach to these LAN destinations A, B, and C. In protocols such as OSPF, there is a feature, just for your information, there is a feature called prefix separation. We'll study about that in later like OSPF section. This feature prefix separation allows us just to use one command, like go under router OSPF, use the command prefix separation. This prefix separation feature allows us to suppress these transit subnet information from the routing table, so that the overall size of the routing table gets reduced significantly. Okay, so in that case, we'll talk about that. But we actually do not need those transit subnet information in order to reach from LAN to LAN. How we will ping the router interface from router 1 to router 3? We will not be able to ping. Like if I'm suppose, for example, sitting at router 1, I cannot ping this interface because I don't have that route in my routing table. And I don't need to actually, honestly. Since you have the route to reach to this destination, if you want to take the access of this router, telnet, SSH, whatever, you can just ping this interface. You can just, take the SSH, telnet based on that IP address. So we should use this command only and only when there is a condition that these transit subnet information should not be available in your routing table to reduce the overall size of the routing table. You have to be very careful with these kind of configurations, even in case of static routing. If you don't give the route to reach to that destination, remember, you will not be able to ping this, you will not be able to ping this. If there is a requirement that you have to ping to those IP addresses, then actually you should obviously configure the routes. But if there is a requirement that you should only be able to ping from LAN to LAN, you don't actually need to give any route in your routing table to reach out to those destinations, so you can skip it. So it's completely dependent, it's completely based on what they have asked you to do that, maybe in the lab, maybe in your production environment. There comes a requirement, for example, they might give you questions such as, in the data center, we have like 10, 20 routers, all those routers are interconnected to each other. And since on the data center, we are running different applications, I don't want those transit subnets to be maintained by the routers in the routing table. Why? Just so we can reduce the overall size of the routing table and save some resources. If that is some kind of condition and you have to perform routing based on protocols such as OSPF, use this feature. But otherwise, unless otherwise you are specified to do that, don't do that. But I was just telling you that if you are sitting at router 1 LAN PC, you don't actually need to give this route information or this route information in order to reach out to this destination or this PC is going to send the traffic to gateway, which is router 1. Router 1 will check the destination IP. Based on the destination IP, the packet will be forwarded to the next hop, which is router 2. Router 2 will check the destination IP. Destination IP is not this. Destination IP is not this. Destination IP is this. And to go to that destination, the next hop is router 3. So packet can be routed towards router 3 based on the entry. So we don't actually need any, routes to reach out to those transit subnets in order to reach LAN to LAN. They might give you some sort of, conditions that, okay, you have to perform the routing, but you don't actually have to, maintain the transit subnet information in your routing table. If they do that, you can remember this feature called prefix separation. We'll talk about this in more detail. If you are doing static routing, just don't do the routing for subnet D, subnet E, which are the transit subnets between router 1, router 2, router 2. Fine. So what is routing? Exactly. Like when you do this, IP routing keyword, when you use that IP routing keyword, do not use that command IP route for the subnet D, for the subnet E. There's no need for that. You can just do the routing for B. You can just do the routing for C. And the packets will still be delivered to the destinations. We'll do that practically. This is the same topology that we will follow. We'll do that. So what is routing? Routing is a process of forwarding the traffic from one network to another network. Basically, routing is a process of moving the packet from one interface to other interface based on destination IP address. So based on destination IP address, moving of the packet from one interface to other interface is what we call routing. And whatever devices are capable of doing that, those devices are basically called like routing capable devices or layer 3 devices. A very commonly utilized layer 3 device, as you already know, is a router. We can also use a layer 3 switch. So we can also perform the routing on firewalls and some other appliances as well. So any device, that can take a packet on one interface and route the packet towards out of the other interface towards a particular destination. That's what we say that the device is capable of performing. By default, a router will perform routing for directly connected networks only, because routers, they know about those directly connected networks because they are automatically maintained in the routing table as soon as we configure the IP address onto these interface. Router by default, they do not know indirectly connected subnet information. For that, we have to do something. Like either we can give those indirectly connected subnet information, like we can tell the router how to reach to those destinations statically, or I can tell the router to dynamically exchange that information with the other router based on some dynamic routing. Why we need routing protocols? Because doing static routing everywhere is not a very good idea. If your network is quite big, if you have a big network, in that big network, it's not possible to perform static routing completely by yourself. That's why we need some routing protocols. And there are two types of routing protocol that we can utilize in our production environment. One routing protocol that we can use are called IGP or interior gateway protocols. And the other type of routing protocols that we can use are called EGP, exterior gateway protocols. So if we define routing, like routing can be done either statically or dynamically. And dynamically, we have IGP, then we have EGP. In EGP, the only protocol that we have nowadays is BGP. Earlier, we had a protocol such as EGP. Before that, we had the protocol GGP, gateway to gateway protocol. Then it came like EGP. EGP was a protocol in itself it as well. I believe Department of Defense has been using like EGP for quite long time, but now everything has moved towards the BGP. And current BGP version that is going on is BGP version. Under the IGP protocol, we have protocols such as that comes in the category such as distance vector and link state. We'll talk about them just in a moment. So how can we differentiate like which protocols are IGP protocols and which protocols are EGP protocols? To differentiate between IGP and EGP protocol, we have to understand the concept of autonomous system. So a network of interconnected routers and related systems, which could include switches, PCs, firewalls, and everything managed under a common network administration is known as one autonomous system or one routing domain. So one autonomous system is a group of devices, group of routers, not only routers, group of routers, switches, firewalls, security appliances, PCs, servers, and everything under a common network administration. So a group of devices, a group of internetworking devices under a common administration is called one autonomous system or one routing domain. In some places, an autonomous system is also defined by the property that a group of devices exchanging the routes information via common routing protocol, they come under one autonomous system. Such as if you are running OSPF completely in my autonomous system, that will come under one single autonomous system such as that. But this is much more better definition for the autonomous system. A group of devices under a common administration can be represented by one single number, and that single number is going to be known as the autonomous system. A routing protocol and routed protocols. See, the use of the routing protocol, is to carry the routes information from one router to another router. Routing protocols are responsible to carry the routes information from one router to another router. On the other hand, the routed protocols are the protocols that are responsible to carry the data. They are responsible to encapsulate the data. The routed protocols are those protocols which are responsible to encapsulate the data and carry them over the decided best path. So routing protocols are responsible to exchange the routes information from one router to another router, and routed protocols are responsible to routing protocols are responsible to select one best path to reach out to a destination, and it is the routed protocol which are responsible to carry the data over the selected best path. So routing protocols such as RIP, EIGRP, OSPF, BGP, ISIS, these are the routing protocols. When it comes to routed protocols, we have three routed protocols. One is IP, one is IPX, and one is AppleTalk. So these were three routed protocols that we were using in earlier days. IP in TCP/IP protocols stack, IPX, there was a protocol stack. There was an internet networking model called IPX, SPX networking model. They were using IPX instead of internet packet exchanged and sequential packet exchanged. They were using this IPX instead of IP. And Apple Talk, as you might have guessed, on the Apple devices. So on Apple systems, they had a dedicated protocol suite called Apple Talk to carry the data from one Apple device to other Apple device. Nowadays, IPX and Apple Talk, these are considered as legacy protocols. So the only protocol that you will notice being used to carry the data from one router to another router, one device to another device, is IP. So routing protocols are those protocols which are responsible to carry the routes, decide the best path to reach out to a destination. And routed protocols are those protocols which are responsible to carry the data, encapsulate the data, and carry it over the selected best path from one device to another device. So routed protocols perform encapsulation, and routing protocols, they actually carry the routes information from one router, from one device to another device. Now, so we have one autonomous system. Let's represent that autonomous system with the number 100. Then we have another autonomous system. Let's represent that autonomous system with the number 200. Under this autonomous system, we have a few devices. I'm going to just consider routers for the moment. And in this autonomous system, we also have few devices. One autonomous system can have more than one device. One autonomous system can have only one device. It does not matter how many number of devices are there in one autonomous system. So one autonomous system is group of routers and interconnected devices managed by a single network, single administration. A group of devices managed by a single administrative authority is called one autonomous system. So when we have to perform the routing within the autonomous system, or when we have to perform intra-autonomous system routing, we are going to use the IGP protocols, interior gateway protocols. IGP protocols or interior gateway protocols are responsible to perform the routing within the autonomous system. We can use one IGP protocol, such as, we can use RIP version 2, we can use EIGRP, we can use OSPF, we can use ISIS. All of these protocols are actually, in fact, interior gateway protocols. These protocols are responsible to perform the routing within the autonomous system. And when we have to connect two or more autonomous systems, the only option that we get nowadays when it comes to inter-AS routing, to perform the inter-AS routing, the only option that we get nowadays is a BGP. So BGP is the only protocol that you might notice being used between two or more autonomous systems to carry the routes. So when it comes to inter-AS routing, the only EGP protocol that we use is BGP. So IGP protocols are responsible to perform the routing within the autonomous system. In short, for intra-AS routing, use IGP. For inter-AS routing, use EGP. The only EGP protocol that we will get nowadays is BGP. It's not like IGP protocols cannot act as EGP and we cannot use EGP as IGP. It's not like that. Let's say, if you're specifically talking about BGP, BGP is a protocol that can carry very large amount of routes from one autonomous system to another autonomous system, routes in approximate millions. At the moment, like last time I checked, there were approximately 900,000 routes in the BGP routing table. They are like close to 1 million. The point is, BGP is a protocol that can carry a large amount of routes information from one end to another end. So why cannot it carry like 5,000, 6,000 routes within the same autonomous system? It can actually. So we can use BGP as both. We can use BGP as IGP. We can use BGP as EGP. We can use BGP within the autonomous system. We can use BGP in between the autonomous system. One flavor of BGP is what we call IBGP. One flavor of the BGP is what we call EBGP. So BGP can run in both the sides, like IBGP and EBGP. BGP can run as both. So, BGP can work as both. BGP can work as EGP protocol and BGP can work, I will try to slow down. Okay, I will try to slow down. BGP can work as like both. BGP can work as both, like IGP protocol. Like when we use BGP as interior gateway protocol, we refer to that as IBGP. And when we use BGP as exterior gateway protocol, we call the BGP as EBGP. So BGP can work as both. Like BGP can be used as both IGP and EBGP, like EGP. But the point is, like, BGP is designed to act as an EGP protocol. BGP is designed to act as a protocol that runs between the autonomous system. So if you are going to use BGP as IGP, such as like in case of IBGP, if you are going to use BGP as IBGP, there are specific conditions, there are specific scenarios, when you actually have to use IBGP in your infrastructure. There are specific type of designs, there are specific designs where you should consider using IBGP. But generally, when it comes to perform the routing within the autonomous system, we are not going to use IBGP. We are going to use IGP instead. See, IGP protocols are designed to act as an IGP protocol. So we can use IGP as EGP, but IGP protocols are not capable of carrying a large amount of routes. Like as per the considerations, like let's talk about OSPF. I consider OSPF as a best possible protocol for your infrastructure environment. So the point is that, let's say you are using OSPF as a routing protocol. If you are using OSPF in your production environment, for a stable operation of OSPF, it is advised that you should not have more than 6 to 8,000 routes in your routing table. Like if you have like more than 6 to 8,000 routes in your routing table, you might face here and there some issues in OSPF routing. However, modern day routers, they are capable of like handling the routes approximately 40,000, 50,000 routes using IGP. But for a stable operation, it's not advised. It's not advised that you have more than 6,000 to 8,000 routes in your IGP routing table using protocols such as OSPF, using protocols such as EIGRP. Like modern day processors on the routers, they are capable. Modern day routing protocols like OSPF, EIGRP, they are capable of handling like 40,000, 50,000 routes, but the limit remains the same, like 8,000, 6,000, 8,000 maximum. So if we have more than 6,000, 8,000 routes to exchange between two routers, let them be in the same autonomous system, in a different autonomous system, go for BGP. But if we have like less than 6,000 to 8,000 routes to handle, even in between two or more different autonomous systems, don't go for BGP. Go for some other protocols, some other IGP protocols such as EIGRP, such as OSPF. So it all comes like, in my opinion, it all comes like how many number of routes you actually have to exchange. How many number of routes you actually have to exchange from one router to another router. Based on that, you will choose like one routing protocol that is suitable for your environment. There are other factors as well. For example, your favorite protocol is ISIS, and in your company, no one knows ISIS. So you cannot implement ISIS in your production environment, because just in case if any problem arrives, you will be the only one to troubleshoot that ISIS connectivity. So there are a lot of factors that decide like which IGP protocol or like which EGP protocol we have to use in our production environment. Number of routes that a protocol can handle is one of the factors. The other factor, for example, is the protocol proprietary, or if the protocol open standard. Do you have Cisco devices? Do you have non-Cisco devices? Like your IT staff, your IT staff is familiar with which protocol. Like maybe your IT staff is familiar with EIGRP and OSPF. So you should consider implementing EIGRP and OSPF, not the ISIS protocol, not the RIP version 2. Is the protocol support subnetting, supernetting or not? Maybe you are using RIP version 1 that does not support these kind of features. So there are a lot of factors that you must actually consider before you decide to choose one protocol. Number of routes that a protocol can handle, like it is just one of the. So we have these routing protocols. We have RIP, we have EIGRP, we have OSPF, we have ISIS, we have BGP. These are the protocols that we can. Yes, route redistribution, and a lot of things are different in ISIS protocol actually. Like we'll talk about ISIS a little bit when we talk about OSPF. But see, OSPF and ISIS both are linked state routing protocol. Both can be used within the autonomous system. Both use SPF. Like both use link state database. There are a lot of similarities between OSPF and ISIS, but here and there you will notice there are a lot of differences between OSPF and ISIS as well. One of the biggest advantage of using ISIS in a production environment, in a service provider environment, for example, is that ISIS does not have any dependency on area 0. That remains the single most important concept in ISIS. Unlike OSPF, where all the non-backbone areas must be connected with the backbone area, ISIS does not have any such requirement.
The way we design the topology in ISIS is completely different than OSPF. Like, in OSPF, we actually design the areas like that. Let me show you. We design the area like that. This network is part of one area. This network is part of one area. This network is part of one area. In ISIS, we define that, oh, these routers are part of one area. This is part of another area. It is possible that this is part of one area and this is part of another area. In OSPF, it is not possible. So the point is that from the design point of view, you will notice there is a difference in OSPF and ISIS configuration. But one of the biggest advantage of using the ISIS is that it is not dependent on area 0. So if you have a service provider environment, let's say, for example, Airtel, Geo, for example, which has span across like India, like every state, like every city has connectivity using Geo, Airtel, and these service providers, for example. So they are covering very large geographical area. They must have created some branches, some headquarters, and all those type of things. So if they try to implement protocols such as OSPF, they have to have a centralized area 0, then they have to connect everything to area 0 using physical media, virtual link, and everything. But if they use ISIS, there is no such requirement. That's why you must have noticed that a lot of service providers, they still prefer ISIS in their production environment instead of using OSPF. However, if you know OSPF, you know half of the ISIS, but from the design and configuration point of view, things are going to be different. So we'll talk about a little bit of ISIS later on, but all of them comes under the IGP category. The only protocol that comes under EGP is BGP. Protocols other than BGP are designed to operate within the autonomous system. That's why they are known as interior gateway protocols. Exterior gateway protocols are designed to route between different autonomous systems. BGP is the mostly used exterior gateway protocol, and it can also be used within the autonomous system in the flavor of IE-BGP. So BGP can run within the autonomous system in the name of with the name of IBGP, and BGP can run in between the autonomous system. And in that case, we refer to it as EBGP, exterior BGP. Now, all these protocols that we have listed here represent to EIGRP, OSPF, ISIS, BGP. All these protocols must work on some algorithm, which is responsible to, exchange the route, decide the best path, loop avoidance, and all those things. So all these protocols that we have listed here, such as represent to EIGRP, OSPF, they must work on some algorithm. Now, both EGP and IGP use different algorithm for path selection. For example, distance vector algorithm, enhanced distance vector algorithm, link state algorithm, path vector algorithm. So distance vector algorithm is used by distance vector routing protocol, such as RIP, version 2, version 1, IGRP. Enhanced distance vector algorithm is used by the protocol EIGRP. Link state algorithm is used by the protocol OSPF ISIS, and path vector algorithm is run by the protocol BGP. Once a router receives the routes from various paths, it selects one of the best path to install in the routing table, and it uses a few criteria to select the best path. This is important. Let's talk about this for the moment. So this we have already explained that within the autonomous system, we can run the IGP protocol such as OSPF, EIGRP, IBGP, ISIS. We can use these protocols to run within the autonomous system, but you really don't get any choice other than BGP when it comes to perform routing in between the autonomous system. BGP can be used as both eBGP and IBGP. Within intra and inter, BGP can be used for both. It's advised, unless certain conditions are there, we'll talk about those conditions, do not use IBGP. You prefer OSPF, prefer EIGRP, prefer ISIS. Unless certain conditions meet, don't use IBGP. We'll talk about those conditions in BGP section. About this, once a router receives a route from various paths, it selects the best path to install in the routing table, and it uses a few criteria to select one best path to be installed in the routing table. This thing, let's talk about. This is a router, and this router gets two paths. Like if it has to go to, let's say, this destination. If the router has to go to this destination, the router has received the information from, let's say, two of the neighbor router number 2 and router number 3. Now this router has to decide one of the best path to reach out to that destination, and that best path will get installed in the routing table. Now the question is, which path gets to install in the routing table? So first criteria. Acha, one more thing I would like to clear, which path gets to install in the routing table and which path router takes to route the traffic. These are two completely different things. Actually, you will understand the difference. So first of all, let's talk about which path will become the best path and gets installed in the routing table. So what is the first criteria based on which the router is going to choose the best path to be installed in the routing table, not the best path to route the traffic. These are two different things. We are talking about the best path to be installed in the routing table. We are not talking about the best path to route the traffic. These are two different things. Don't get confused with them. So we are talking about this at the moment. So the first criteria, as you already know, the first criteria the router uses to decide which path gets installed in the routing table is what Robert said, prefix length. Okay. Anyone else who thinks that prefix length is the first thing that the router decides or the router selects? The first thing that the route, see, we have studied this. First of all, prefix length, then AD, then metric, and then what happens? Load balancing. This thing that you have studied, this like prefix length, AD, metric, and load balancing, this criteria, these four criteria are when the router decides the best path to route the traffic, not this. If we have to go to this destination, let me tell you, if we have to go to this destination, let me represent exact destination. Let's call that 10.1.1.0. Okay. Let's say you have to go to that destination, and to go to that destination, you are receiving the route from here and you are receiving the route from here. Okay. From here, when you are receiving the route is being received as 10.1.0.0/16. And from here, when you are receiving the route is being received as 10.1.1.0/24. Which one will get installed in the routing table? Quickly, everyone. Router 1 receives a route to reach out to that destination 10.1.0.0.0/16 from one, 24 from the other, which will get installed in the routing table. As you might have guessed that based on highest CIDR, /24 will get to install in the routing table. You can also think that /16 might get installed in the routing table, but the answer is both of them will get installed in the routing table. This criteria is not applicable for route selection. This criteria is only applicable when the router decides which path it has to take to route the traffic, not which path it has to install in the routing table. Think about it. This represents a different range. Think about it. This represents this range. If you know subnetting and everything, this represents a different range. If the router installs the route in the routing table, let's say if the router installs this route in the routing table, the router will only be able to reach out to these destinations. But apart from these destinations, there are other destinations that are covered in the route. So this makes much more better choice to install in this route in the routing table, because it covers a large subnet as compared to this one. But again, on the other hand, this is more specific as compared to this one. If you have to go to this destination 10.1.1.99, if you have to go to this destination 10.1.1.99, you will find this destination faster in this route as compared to this route. I will prove that in a moment. But the point is, this route that you have received via router 2 covers a longer range of destination as compared to this one. So router will actually install both of the routes in the routing table. I'm not saying which route it will prefer to route the traffic. I'm saying that the router will install both the routes in the routing table, because this covers a different range, this covers a different range. Questions? Let me know. Anyone? Raise hand. I will unmute just in case if you don't understand this. Why the router installs both the routes in the routing table? Because both the routes actually cover a different subnet. Both the routes cover a different range. /16 covers the range 10.1.0.0 to 10.1.255.255, which is a different range as compared to 10.1.1.0 to 10.1.1.255. No, this is not the same range. These are two different ranges. /16 covers a bigger range as compared to this one. You can say this comes under this. All of these destinations are included in this one. So even if the router installs only this route, it's okay. But this is more specific. If you have to go to just these destinations, this is the best possible path that you can take. So you can argue that the router will install /16, the router can install /24, but the fact is the router will install both. You can test it in your lab environment if you want. Just create a topology, just create a simple topology, router 1, router 2, router 3, and try to advertise the same subnet from both the sides, from one side /16, from one side /24. Forget about for the moment, Amit, forget about for the moment the routing protocols and all those things. Forget about that. This could be received by EIGRP. This could be received by OSPF. I don't care actually. That factor like which routing protocol, like, you know, based on AD value, EIGRP is better, OSPF is not better. That criteria will not even come into the picture. The first thing that the router is going to look up is the CIDR, but it will not decide which path it has to install in the routing table based on the CIDR. So you guys were half correct. Like, it checks the CIDR, it checks the longest prefix match, but it will not install the route based on that in the routing table. You can create this topology, you can do the experiment, and you will notice that the router 1 will install both the routes, even if one is coming from EIGRP, one is coming from OSPF. And the reason for that is that these are two actually different subnets. These are two different ranges. Let's say both were on /24. Now it has to choose one, because 10.1.1.0/24 you are receiving from both the sides, from here and from here. Now the router, since both the routes represent the same range and to go to the same destination, now the router will choose one of them as the best one. Now it will go to AD value. Now it will check, oh, one route is from EIGRP, so AD is 90. One route is from OSPF, so AD is 110. So now I will install this route in my routing table. I will not install this route in the routing table. So the second criteria, AD, comes into the picture. So actually, when it comes like which path gets to install in the routing table, AD is the first thing that is there, not the CIDR. If the CIDR is different, both the routes will get installed in the routing table. If the CIDR is same, then the router will compare to see which path is better based on administrative distance value. What if both of them are from EIGRP, like EIGRP, same AD? Then it will go to the third criteria, which you already know is metric. And if the metric is same, let's say from here the metric is 100, from here the metric is 100, then it will perform load balancing. We call that equal cost multipath, ECMP. Equal cost load balancing it will perform. Means like, let's say you send 10 packets, so 5 packets from here, 5 packets from here. So equal cost multipath it will perform. It does not happen exactly like that, but just for now, let's consider it happens like this. So the first criteria in route selection is not prefix length. First criteria in route selection is AD. Whichever path has lowest AD gets to install in the routing table. If the AD comes same, then the second criteria metric, and if the metric comes same, then the third, then the last final criteria is the load balancing. And that type of load balancing is what we are going to say as equal cost multipath, ECMP. Now, let's say on one side you are receiving the route on /16, on the other side you are receiving the route on /24. You install both the route in your routing table. You install this route as well as you installed this route in your routing table. Why? Because they both represent a different subnet. Now, when the packet arrives on the router interface, the packet has a destination 10.1.1.99. Now the router 1 will check, if I have to go to that destination, I actually have two paths. One path is on /24 and one path is on /16. So which path should I choose? Now it will choose the path with the higher CIDR. These are two completely different things. Which path gets to install in the routing table versus which path is taken to route the traffic. These are two completely different things. CIDR will not come into the picture when we talk about route installation in the routing table. CIDR will only come into the picture when we talk about traffic forwarding, data forwarding. And why? Why this? Why this /24 is preferred over /16? Because let's convert this in binary, okay? And let's convert this in binary. And let's convert this in binary. You will notice if you compare this with this, you will notice once you compare them bit by bit, you will notice that 24 bits are going to match as it is. And if you compare this and this bit by bit, you will notice that only 16 bits are going to match as it is. So the router has to search, in case of this, the router has to search for that destination in how many routes? Approximately 2 raised to the power 16 number of destinations. Because slash 16 means 16 bits for network and 16 bits for host. So in this range, how many number of hosts are there? 2 raised to the power 16 number of hosts are there. So the router has to search this destination in this much amount of hosts. And if you talk about this, how many number of destinations are there? Just 2 raised to the power 8. So the router has to search only in 256 number of destinations. So why the longer CIDR is preferred as compared to this shorter CIDR? Because when the router performs bit by bit comparison, between the destination IP and the route, it will always select that path which matches with longer, bits, 24 bits if are same versus if 16 bits are same, it will always prefer 24 because there it has to search in less number of destinations as compared to. That's why highest CIDR is always preferred. If the CIDR was same, then the router would have gone to AD value. If the AD is same, then the router would have gone to the metric value. If the metric is same, then the router would have performed the load balancing, equal cost multi. So these are two different things. Route selection and which path is the best path to perform the traffic forwarding. These are two different things. Which brings me to another question. Okay, what about this? Okay, what about this? Okay, let's consider whatever subnet. This is the topology. This is the topology. This is loopback and everything. I have configured RIP. I have configured EIGRP. And I have configured OSPF. I have configured all the protocols on router 1 and router. Basically, these routers can exchange the routes via RIP. These routers can exchange the route via EIGRP, and these routers will, in fact, exchange the routes via OSPF. I know RIP has the AD value of 120. EIGRP has an AD value of 90 and OSPF has an AD value of 110. When the router 1 advertises this route information to router 2 via RIP, via EIGRP, via OSPF, obviously the CIDR is same. So router will see which of the AD value is lowest. So it will choose of course, like EIGRP route will get installed in the routing table. Same goes here as well. Like when this subnet is advertised to the neighbor router, it is being advertised via RIP, it is being advertised via EIGRP, it is being advertised via OSPF. Since CIDR is same, /32/32/32, it will go to the AD value, and since EIGRP has the lowest AD value, so route will get installed in the routing table via EIGRP. My question is, what if I configure the same AD value for all the protocols? Let's say 100. I went under router RIP. I configured distance 100. I went under router EIGRP. I configured distance 100. I went under router OSPF and I configured distance 100. Then which path it will choose? Which route will be installed in the routing table? EIGRP, RIP, or OSPF? Remember, all of them have the same AD, and you cannot say that AD is same, so it will go to the metric value. You cannot compare EIGRP metric with RIP metric. That's why we had the AD value. We cannot compare EIGRP metric, which is composite metric, with hop count. EIGRP metric is a very big number. Hop count is just like 1 to 15. OSPF has cost. We cannot compare the metric value. We cannot compare the metric value for the routing protocol. That's why we needed AD value as a common ground based on which we can compare the routing protocols. On the scalability, like on the reliability scale, EIGRP is more reliable than OSPF and RIP as per the AD value. So now my question is, if I put that on the reliability scale, if I put all those routing protocols on the same AD, then which one it will choose? That could be one of the answers, that it will choose all of them. But if it installs all the routes in the routing table, it will increase the size of the routing table again. And it does not make any sense to install all these 3 routes in the routing table because all these 3 routes are same destinations. So it does not make any sense actually. Let me know. Anyone, any idea? Okay, I will not tell you the answer for this one. You can search for this. You will let me know the answer anytime you need. No, the load balance it will not do. RIP it will not do. It will not use RIP. It will not select the bandwidth. No. Do the experiment and let me know. It will not use OSPF. Don't do this, na. Someone said OSPF, someone said EIGRP, someone said RIP. One of them will be correct, na. So don't answer like that. I will not tell you the answer. Okay. You will do one thing. You will create this topology. See, OSPF and RIP is incorrect. So only one option is remaining. That is EIGRP. Okay, so of course it will install EIGRP in the routing table, but the reason is why. So if I put same AD value for all the protocol, it will install EIGRP in the routing table. That is the answer. Now you have to search why. You can do this. You can create a topology on packet tracer. You can create this topology on GNS if you want. Same topology. Try to configure the routing protocols. You already know how to configure EIGRP OSPF. Maybe you know how to configure RIP, router RIP, or don't configure RIP, does not matter. And see which protocol it chooses. Configure the same AD value for EIGRP or OSPF. It will choose EIGRP. That is the answer. But the question is why? No. That is not the answer, Kavita. That is not the answer. The answer was like one of the answer was that because the EIGRP has more parameters in the best path selection, but that is not the case. Because of the algorithm, that is not the case. Okay, you try to study. Okay, you try to find out the answer for that, and you let me know whenever you can. Answer is EIGRP. Why? You have to study. Now, one more thing about the AD value. About the AD value, one more thing. AD is actually not universal. AD is not universal on all the vendor. AD is different on different vendors. Anyone who has worked on Juniper devices, anyone who has worked on any other vendor, HP, Huawei, all these vendors, Nokia, Alcatel, Cisco. AD is not universal everywhere. So I can show you one chart if you want. What I'm trying to say, that the administrative distance value, okay, administrative distance value, what is the AD value? First of all, what is the AD value? AD value, administrative distance value, is trustworthiness of a routing information source. So if we have received a route via EIGRP, let's say you have received a route via EIGRP, how trustworthy, how reliable that information actually is. If you have received the route via, let's say, OSPF, how reliable that information actually is, that is decided by the AD value. So AD value is just administrative distance, because we cannot compare the protocols based on metric, because every protocol works on a different algorithm and every protocol has a different way of calculating the best path. Like for example, OSPF uses cost, EIGRP uses composite metric, RIP uses hop count, ISIs have some other criteria parameter. You know about BGP. If you know about BGP has the path attributes. So since all the protocols that we know, they use different criteria to select the best path, we cannot compare them based on metric value. That's why we needed a common ground based on which things can be compared, and that's why we had the AD value. So administrative distance value, or the AD value, defines the trustworthiness of a routing information source. So if you have received a route, like if you have received the route via EIGRP versus you have received the route via OSPF, which one will you choose? That is defined by the AD value. Lower AD is always preferred. But the point I'm trying to make is that AD is not universal. As you can see, for the RIP routing protocol, AD value is 120 on Cisco devices, but on the Juniper devices, it is 100. For the HP devices, it is 100. For the Huawei, it is 100. For the static routes, in the Cisco AD value is 1, Juniper AD value is 5, HP's AD value 1, Huawei's AD value 60. They don't even call that AD. They call that route preference, preference. EIGRP, of course, is not applicable on other vendors. EIGRP is a Cisco proprietary protocol. It was a Cisco proprietary protocol. In 2013, it was released as an open standard protocol, but no one has actually implemented it in their operating system. So it's like Cisco only protocol nowadays. Means everyone can implement it, but no one has implemented it. Because they know that if they implement the IGRP, then they have to do the troubleshooting bugs and everything. Because Cisco has, they have given an RFC. There is an RFC on the internet. So you can, if you search this RFC, it will tell you everything about EIGRP. But since EIGRP was created by Cisco, they will not tell you about the bugs, all the problems that they have faced for so many years. So if you decide, if Juniper, if in the Juniper operating system, if in the Junos, they decide to implement EIGRP, they decide to encode EIGRP in their operating system, then they also have to face the issues like bugs and everything. EIGRP might not work properly, then they have to, ask the developer to fix those issues and all. So it's a very hectic process. So no one actually has implemented EIGRP in their operating system. So even though it has gone open standard in 2013, no one actually has implemented it. So it's no longer proprietary, it's open standard. But since no one has implemented it, it's more like a Cisco only protocol. You will only see this on Cisco. You can implement it, but no one has implemented it. You can see the AD value for OSPF. So the point I'm trying to make is that AD, administrative distance value, is only on Cisco devices. On the other vendors such as Juniper, HP, Huawei, they call that route preference or in fact preference. Which brings me to another question. What if this is one router and this is another router? Same /32 subnet here, /32 subnet here, whatever subnet you want to take. This is a Cisco device and this is, let's say, a Juniper device. Okay. Or let me take, okay, I don't have any other option. Juniper device, let us consider. Now, let's say I configure here, let's say I have configured RIP, okay, and OSPF on here. And I have configured RIP and OSPF here as well. Okay. Both the routers have, because RIP and OSPF both are open standard protocol, so completely we can implement, we can run. Both the routers have exchanged the routes via both RIP and OSPF, both the routing protocols. As per the Cisco device, RIP routes have the AD value of 120 and OSPF routes have the AD value of 110, which basically means that Cisco device will choose OSPF route over RIP route. It will install this subnet information in the routing table via OSPF. Let's say on the Juniper device, you can see on the Juniper device the AD value for this is 100, for example. And let's say for OSPF the AD value is let's say 150. They are, or we have incremented the AD value to whatever it is. It does not matter. Now my question is, if this router decides to install the route via RIP, this router decides to install the route via OSPF, will there be a communication between these two devices or not? If on one router the route is installed via OSPF, on the other router the route is installed via RIP in the routing table, will we be able to communicate from LAN to LAN or not? Does it actually matter which routing protocol gets to install the route in the routing table? It actually does not matter. Till you have a route in your routing table, you will be able to perform the routing. So it does not matter if we have learned the route via OSPF, we have learned the route via RIP. till you have the routes in the routing table, it will just work fine. Obviously, you cannot do this, that you configure OSPF only and you configure RIP only, then OSPF and RIP cannot exchange the route. But let's say we are running multiple routing protocols. It does not actually matter which routing protocol gets to install the route in the routing table. Till there is a route in the routing table, your communication will be okay. So administrative distance value AD value come into the picture when the router has to decide the path to reach out to a destination that are coming from maybe different routing information source, such as EIGRP, such as OSPF. Then it will compare one of them and it will install one of the path in the routing table. And also think about it, Cisco had a protocol called EIGRP, which was a proprietary protocol to Cisco. EIGRP was a Cisco proprietary protocol. So let's say you have the option to run EIGRP, OSPF, BGP, all the protocols. As a vendor, why will not I prefer my own routing protocol over the other routing protocol? I will ask my developers to give a preference to EIGRP at the very top and put all the other protocols on the bottom. The point is, as a vendor, it's completely on me. It's completely on me which protocol actually I prefer to install the route in the routing table. If I want, EIGRP is my protocol. I developed EIGRP. So why will I prefer OSPF in my routing table? I will encourage everyone to use EIGRP so that they purchase Cisco devices. So the point is that I will prefer EIGRP route over the other route. So it's AD value defines the preference of the operating system to choose one protocol over another protocol. And it's completely onto the vendor. It's completely onto the vendor which protocol they actually go for. Actually. No, Napoleon, it will not work. If you have, like, for example, if you are running RIP here and if you are running OSPF here, for example, and you do the redistribution and everything, it will not work because first of all, there will not be any route exchange between them. So you cannot actually redistribute the things. So it will not work. EIGRP is the fastest protocol to converge. Yes, that is true. EIGRP is the fastest protocol to converge, but EIGRP lacks a few features that are required in a service provider environment, such as traffic engineering. So it is not a very preferred choice for a service provider environment. But overall, EIGRP is best. If you have Cisco devices, EIGRP is the best option that you can go for. How this communication will happen? It will not happen actually, unless you do this. You configure RIP here, and then you configure OSPF here, and then you perform redistribution. Okay. And this gives you your answer. This gives you your answer why EIGRP will be preferred if you configured all the protocols. If you have configured all the protocols with the same AD value, it will go to the default AD values, and the default AD values based on the Cisco iOS, EIGRP will win. That's why EIGRP route will get installed in the routing table. If it was another vendor such as Juniper or another, you would have seen based on the default preference, the route will get installed in the routing table. So yes, that answer was correct. We can change the AD value manually if we have to select one path over another path. For example, let's say for example, we have multiple paths to go to the destination. Okay, and I want to prefer this path over this path. Maybe both the paths are coming from EIGRP only. So I can change the AD value from this path as lower. I can purposefully change the AD value from this path as higher, so that the router choose this path over this path. That was just for test. That was just for testing. the question that I asked, that if everyone has the same AD value, then which one it will go? It will go to the default AD values. That's what just for your knowledge. So AD, administrative distance, defines the preference of the operating system to install the route in the routing table via a certain routing protocol. Administrative distance defines the trustworthiness of the routing information source. Who will define which routing protocol is more trustworthy, less trustworthy? The vendor will decide. Obviously, Cisco will decide that EIGRP is more trustworthy than others. Why? Because EIGRP is their protocol. So other vendors might define other vendors. For example, Juniper has decided that static routing is most reliable. Then I will choose, for example, OSPF. Then I will go for RIP and so on. So AD, trustworthiness of routing information source. It's on to the vendor which one they actually prefer. AD is not universal. AD is something that gets changed from vendor to vendor. Based on the administrative distance value, we can choose one path over the another path. We can do some sort of path manipulation, best path selection, and all that. Since AD is the criteria based on which the router decides the best path, AD is the criteria based on which we can manipulate the best path as well. We will do that in route manipulation techniques. So hope now the AD makes sense. Administrative distance value, prefix length, it makes sense. After the AD value, it will go to the metric. And if the metric is same, it will perform the load balancing. If the metric is not the same, lower is always preferred. So higher CIDR, yeah, longest prefix match, then the lowest AD and the lowest metric value is always preferred. Any questions so far? Anyone? Let me know. Just click on raise hand. I will unmute you from my side just in case if anyone has any question. Any point you did not understand, let me know. All right, all good if. So let's continue. Now, as we have covered that all these protocols, they choose different algorithm. So like we have RIP, we have EIGRP, we have OSPF, we have BGP, ISIS, all these protocols, they use different algorithm. So first algorithm or one of the algorithm that the routing protocols can use to decide the best path, loop avoidance and everything is called distance vector algorithm. There are some protocols that use the distance vector algorithm to decide their best path, to advertise the routes and everything. So distance vector algorithm is used by distance vector routing protocols such as RIP to advertise the routes to the neighboring devices. There was also a protocol called I-MEDITA, Interior Gateway Routing Protocol, that also used to come under the distance vector protocol category. But I-MEDITA got obsolete. So the only protocol that you were using as the distance vector routing protocol was RIP. There are two versions for RIP, RIP version 1 and version 2. Version 2 being more popular version than version 1. But it came like after quite a long time. We'll talk about that. But RIP is the distance vector routing protocol, which uses distance vector algorithm to decide the best path and to advertise the routes to the neighbor router. Now, how this distance, see, distance vector, distance, means like the measurement of like how many, what is the distance from source to the destination from a particular path. What is the distance from a source to a destination? From this path, what is the distance from source to the destination? From this path, what is the distance from source to the destination? And vector means direction. So in whichever direction we have the least distance, we have the lowest distance to reach out to the destination, that path will be the best path as per the distance vector algorithm. So distance means like how far away the destination is. The distance is route metric to reach out to the network. We measure the distance in kilometers, meters and all, but when it comes to the routing protocol, distance vector routing protocol, they measure the distance in terms of hop count. Means if I have to go to this destination is how many hops away from this path, for example, and how many hops away from this path, for example. So if I am at router 1 and I have to go to this destination, how many hops away this destination is from this path and how many hops away that destination is from this path, based on this hop limit, whichever path has the least number of hops or lowest number of hops, that will win. So if I go via router 5, total number of hops that we have to take is 2. If I go via router number 2, 3, 4, the total number of hops that we have to take is 3. So hop count means like how many networks you have to change, how many routers you have to cross from source to the destination. So from here we have 2 hops, from here we have 3 hops. So based on distance vector algorithm, this path will be the best path. So distance is the route metric to reach the network measured in terms of hop count, and vector means the interface or direction to reach out to that network, which is like if you have to go to that destination, this is your next hop. After a router receives the route, it stores it in the local routing database. Then it runs the algorithm such as Bellman-Fold or Fold-Flursken algorithm. So distance vector routing protocol, they used Bellman-Fold algorithm or Fold-Flursken algorithm. And based on this algorithm, they determine the best path to reach out to the destination. And that best path selection is done based on the distance and vector. So if we have to go to a destination from one path, the total number of hops are 3. From the other path, the total number of hops are 2. You will choose the path with the least number of hops. So when the router receives the route from different let's say routers, it will choose the path that has least number of hops. Once this router decides that okay, this path is the best path, it will advertise that best path to the neighbor router. That if you have to go to that destination, you can come to me and I can take you towards that destination. The best path is advertised to the neighbor router. Problem with this distance vector routing protocol is that the distance vector routing protocol, they do not have the complete map of the entire network. Means router 4 knows that if it has to go to this destination, it actually has to go to router 1. Router 4 has no visibility. Router 4 in fact has no visibility beyond router number 1. The router 4 can only see router 1. Router 4 cannot see beyond router 1. Router 1 has no idea what topology is going on behind router 1. Router 4 only knows that if it has to go to this destination, it has to send all the traffic to router 1 and router 1 will, see what can be done. So since in the distance vector routing protocol, routers, they do not have complete visibility of the network, there are chances of suboptimal routing, there are chances of routing loop, there are chances of pinhole congestion, there are a lot of problems in the distance vector routing protocol. Distance vector routing protocol does not have a complete map of the whole network. Instead, their database reflects that a neighbor router knows how to reach to a destination. You are giving me the information, so you must know how to go to that destination. I trust you. I trust you blindly. I will trust you blindly. If you say you can take me to that destination, I will say okay. Like if you say that I cannot take you to that destination, I will say okay, I will delete that route from my routing table. Point I'm trying to make is that the distance vector routing protocol, they perform something called routing on rumors, which is just a way of saying whatever information I receive from my neighbor, it is correct. If the neighbor says I can take you to that destination, okay. If neighbor says I cannot take you to that destination, okay. Distance vector routing protocol, they work on the fact that neighbor knows how to reach to that destination. If the neighbor is giving me the route to reach out to that destination, neighbor must know how to reach to that destination. So they do not maintain the complete topological map. Their database reflects that a neighbor router knows how to reach to that destination and how far the neighbor is from the destination network. So this neighbor says that if you have to go to that destination, I can take you there, and the total number of hops will be 3 from me to go to that destination. Total number of hops that I will take is 3. So this router will think that if I have to go to that destination, now the total hop is going to be 4 from my side. So distance vector routing protocol, they perform this thing called routing on rumors. They trust the information received from the neighbor blindly, which causes a lot of problems such as routing loop, suboptimal routing, pinhole congestion, a lot of issues it can cause if you use the distance vector routing protocol. But there is also one advantage of not maintaining the entire topological map in your database. The advantage is that you do not require a lot of resources. Since you don't even care what is behind router number 4, you don't care what is behind router number 4, you don't need to maintain the entire topological map and everything. It will not require for the router to have very high CPU or memory to maintain the database. Database will not be very big, so it will require less resources for these protocols to run. That's why these protocols were very popular protocols onto a network, where onto the routers where the total number of the amount of resources, RAM, memory was very less. Distance vector routing protocol, they only support one metric and one metric only. That metric is hop count. Distance vector routing protocol, they do not support any other metric. The only metric that the distance vector routing protocol support is hop count. They do not support any other metric. That is also one problem. You said that this path is the best path because from here the hop count is 3, and this path is not the best path because here the hop count value is 4. But let's say, what if this is Ethernet and this is gigabit Ethernet? Of course, if I had to send 1 GB traffic, that 1 GB traffic will reach much more faster from this path as compared to this path because this is just Ethernet, this is gigabit Ethernet. But since you are using a distance vector routing protocol, they only care about the hop count. They will always choose this path over this path. They will not switch on to the faster path based on the bandwidth, based on the speed. So that is also one problem, that they only support one and one metric only. So distance vector routing protocol, they are preferable into the environment where on your routers, on your devices, resources are very less. You don't have very high CPU, you don't have very like a lot of memory. So if you have more like a low-end router, it is suitable for you to go for these distance vector routing protocols such as RIP. But in most of the cases, modern day routers and switches, they are capable of running protocols such as EIGRP or OSPF. So modern day routers, they are equipped with enough resources, enough CPU, enough RAM. So like modern day devices, modern day networks, they most probably will never use these protocols such as RIP. In fact, we don't even have to talk about RIP routing protocol. It is no longer in your content. They have removed the RIP routing protocol from the content because in fact no one was using it. So sooner or later you will see that the RIP will be completely obsolete. It is gone from most of the network. If anyone still is using, they most probably will replace it with the EIGRP or OSPF sooner or later. But you will notice that RIP routing protocol most probably will obsolete sooner or later, completely obsolete. I personally do not know any company that uses RIP in their infrastructure. In most of the cases, they go for EIGRP or OSPF. Honestly, I do not know any company that is going for RIP. RIP was a very popular protocol for a banking network where we had very low-end routers on a branch and we just want to do basic routing and all. So RIP was a very popular protocol for a banking sector. But nowadays, like since routers have enough resources, RAM, memory, and everything, so they also go for EIGRP or OSPF kind of protocol. A lot of problems are there in the distance vector routing protocol, routing on reamers, routing loop, pinhole congestion, like single metric. So from router 3 point of view, the only thing that the router 3 sees is this and this. Router 3 sees that if it has to go to this destination, this is the best path. That I have to go to router 1, this is the best path. Pinhole congestion, is a problem. See, let me try to explain it. Something like this. Okay. Let's consider that there is a router here. Okay. There is a router here. There is a router here like that. So to go to this destination, we have this path and we have this path. If you notice, from both the path, the hop count is same. If you have to go to this destination, 1, 2, and 3. If you have to go to that destination, 1, 2, and 3. Hop count is same actually. So from the router 3 point of view, if I have to go to that destination, I will go to router 1. From router 1's point of view, if I have to go to that destination, I have actually two paths. One path is gigabit and one path is serial, as you can see. Now let's say if I send 100 packets, router 1 will receive those 100 packets. Router 1 has two paths. Router 1, it has two paths to go to that destination. It will, and since from both the path, the hop count is same actually. So this router will try to perform the load balancing over gigabit and serial path. So it will send out of those 100 packets, it will send 50 packets from here, and it will send, for example, 50 packets from here. Those 50 packets that have, obviously those 50 packets which got sent via this path, they will arrive onto this router early and they will just now wait in the buffer memory, so that once all these 50 packets have been received from this lower path, those packets can be assembled and sent towards the destination. Now, this is a serial link, so it will take some time for those 50 packets to deliver. Meanwhile, the user is sending the traffic continuously. So again, I received 100 packets, 50 packets, 50 packets. Those 50 packets were received onto the router at very fast rate because it was all gigabit, but this was serial. The packets are being sent in a slow rate. Here the routers are waiting in the buffer memory. All the packets that are waiting in the buffer memory, they are waiting for like all the packets to receive so that the packets can be sent towards the destination. After a certain time period, you will notice that this buffer memory will get full and you will face some kind of congestion issue here. This router is waiting for the packets to be received from here. It is not able to forward all those packets towards the destination unless it has received all those packets from both the paths, because it did that load balancing thing. So a problem, this kind of issue where the router's buffer memory, where the router's memory got full just because the packets were waiting in the buffer memory to exit out of the certain interface, this kind of congestion, this kind of problem that you have experienced, this is what we call pinhole congestion. So pinhole congestion actually occurs on the router when the router tries to perform load balancing over unequal speed path. Router tries to perform the load balancing over this path and this path. This was gigabit, this was serial. Packets got delivered at very fast rate onto here, but they cannot be sent out of the exit interface towards the destination. They are just waiting for all those packets to be received from here. And once all the packets are received, then they can be forwarded out of there. So you will notice after some time that the buffer memory that is storing all those packets will get full. You will face all the remaining packets will start getting dropped. So it will cause some kind of congestion onto the router. This kind of congestion is what we refer to as pinhole congestion, and it is a very common problem in these distance vector routing protocol, because there is only one metric. There is only one metric, which is hop count. If the hop count is same, the router will perform the load balancing no matter what speed is. So if the router tries to perform load balancing over unequal speed path, it will cause a congestion onto the router, and that type of congestion is what referred to as pinhole congestion. Very common issue in these distance vector routing protocols. That's why, since modern day routers have enough resources and everything, it's a good idea that you don't go for these distance vector routing protocols. You go for a link state routing protocol. Link state routing protocols, they use a link state algorithm. One of the biggest advantage of using the link state routing protocol over the distance vector routing protocol is that link state routing protocol maintains complete topological map of the network. Like from router 3's point of view, it will have a clear picture. It will have a clear idea about the entire topology. It will not only just see router 1 and router 4, but it can also see router 2. Anyone who has covered OSPF, they know this thing very well. That OSPF is a link state routing protocol, and a link state routing protocol maintains the entire topological database so that every router actually has a complete identical map of the network. Based on that, they can calculate the best path to reach out to the destination. That is one of the biggest advantage of the same. But if every router in your network is going to maintain the entire topological map of your network, it will require, due to having the complete map of the network, these require more CPU and memory than distance vector routing protocol, but they are less prone to routing loop and they make better path decisions. See, if you have entire map of the network, chances of loops are almost none. Let's say you have to go from, let's say Pune to Delhi, and what you have done, let's say you are going from Pune to Delhi, not relying on any Google map or any map. You are just asking people on the road that, okay, if I have to go to Delhi, which path I should take, which path I should take, which path I should take. You are blindly trusting on the information given by those people. There are very good chances that you will go to a particular destination, you will reach out to there, then someone will say that go there, then someone will say go there, and you will come back to the same location. But if you have a topological map of your like your destination, for example, you have opened Google Map, you put the source, you put the destination, then the GPS, the algorithm run, and the GPS it is showing you a correct path from source to a destination. Chances of loops are almost none. So since the link state routing protocol, they maintain the entire topological database, they maintain the complete topological map of the entire network, the chances of routing loop in link state routing protocol is pretty much none. And they also make better path decision because they know, if I go via this path, what is the metric? If I go via this path, what is the metric? Metric is not dependent on hops. Metric is dependent on the speed of the link. So if it is gigabit, it will choose the path that is fastest based on the speed of the link. So link state routing protocol advertise the best route information based on link state and link metric to all the other routers. If the link state comes up, link goes down, these protocols send the update. If the link comes up, they will send the update. If the link goes down, they will send the update. That's why we call them link state protocol. So if the link comes up, the state of the link changed, then they will send the update. If the link state goes down, then they will send the update. That update will include the metric value, that if we have to go to that destination, this is the metric value to reach out to that destination. Metric is based on cost. OSPF and ISIS are these two protocols that come under this category, link state routing protocol category, and they utilize that link state algorithm. OSPF advertisements are called LSA, and ISIS advertisements are called link state path. The naming convention has changed. So in OSPF, we call them LSA. In ISIS, we call them LSP, link state path. A router receives LSA or LSP, they store that in the database, advertise the link state information to the neighbor router as it is. They don't do any changes. And then this information is flooded to entire network. So this router has given the information to router 4 in the format of LSA, in the format of LSP. That router will advertise that information to the rest of the network as it is without doing any changes in that. This router will advertise to this router will advertise to this. Basically, the information will be flooded into the network. And once everyone gets that information, shortest path first algorithm will run on the database, calculate the best path, and install that best path in the routing table. Every router will execute the SPF on the database. Every router will calculate the best path. Every router will install that best path in the routing table, and then it will start forwarding the traffic towards those particular destinations. They decide the best path based on, again, one metric and one metric only, one single metric, that is cost. Cost is based on bandwidth. Again, not speed, bandwidth. You must know what is the difference in between speed and bandwidth. The cost is calculated in OSPF, for example, based on bandwidth of the link, not speed on the link. We are not talking about STP. In STP, it is on speed, it is not on bandwidth. So, for example, in OSPF, the formula is 100 upon bandwidth, not 100 upon speed, actually. STP calculates also the cost, shortest path first algorithm, like in STP, also calculates the best path based on the cost, but there the cost is dependent on speed, not bandwidth. Here it is on bandwidth, not speed. Means like there we will have the speed concept, here we have the bandwidth concept. Bandwidth and speed are two different things. I can go under the serial interface and I can set the bandwidth to 100,000 kbps, but that does not mean that it will send the traffic at 100,000 kbps speed. We'll talk more about that in OSPF section. So some people were using distance vector, some people were using link state. The problem, there were a lot of problem with the distance vector routing protocols such as RIP, but not everyone could use link state routing protocol at that time. Why? Because they had those low-end routers, and on those low-end routers resources were not sufficient to maintain the entire topological database. So we actually had only two options in earlier days. We have the option to go for distance vector protocol, or we had to go to the option of link state routing protocol. Some people who don't care actually about the entire topological database and everything, in the type of network where maintaining the entire topological database does not make any sense, it is not even required, those kind of networks, they can implement distance vector routing protocols. But in a service provider network, for example, where you should know the entire topology so that you can perform things such as traffic engineering. So there it is required that you know the entire topological database and everything. So those kind of networks, they were using the link state protocols. So people that have the enough resources, they were using link state. People that don't have the resources, they were using distance vector. Everything was working fine. Now, Cisco already had created a protocol called EIGRP, Interior Gateway Routing Protocol, which was a distance vector routing protocol. Then came into the market link state routing protocols such as ISIS and OSPF. Now Cisco saw that protocols such as OSPF, ISIS have a lot of advantages, have a lot of properties that can be integrated with the distance vector routing protocols, such as IGRP used to send the updates in every 90 seconds, no matter if there is any change or not. RIP version 2 used to send the update in every 30 seconds, no matter if there is any change or not. It does not matter. Link state routing protocol, on the other hand, they only advertise the change information when the link state has changed. If the link has came up or went down, then only they will send the update. Basically, link state routing protocols, they were sending triggered and incremental updates. Triggered means when some event occurs, like link went down, link came up, a new network got advertised and everything, then they will send the update. As soon as any event has occurred, event has triggered, then they will send the update. And what do we mean by incremental? Incremental means whatever has changed, only that information will be sent, not everything. Distance vector routing protocol, in every 30 seconds, they were exchanging the entire routing table. which was causing a lot of problems. Like, let's say you have 10 Mbps link, and over that 10 Mbps link, in every 30 seconds, you are sending a RIP update message, which is going to contain those 20-25 routes. Every route will be some size. So unnecessarily bandwidth utilization is there. Even though the change has not happened, even though there is no change, but still in every 30 seconds or in 90 seconds in case of IGRP, I'm sending the update. That was a problem. So Cisco, what they did actually, they studied those link state routing protocols, and they took out a few properties of the link state routing protocol. They implemented those properties in the distance vector in their IGRP protocol, and they launched it with the name of enhanced IGRP or EIGRP. They could have just said EIGRP, like they could have just said IGRP version 2. Just like we had RIP version 1, RIP version 2, they could have just said IGRP version 2. But no, they said enhanced IGRP. This is an enhanced distance vector routing protocol. It is going to use enhanced distance vector algorithm. They changed the name of the algorithm to dual, stands for diffusing update algorithm. Why we call that dual, we will study later on. But they changed the name of the algorithm, that they say that, oh, it is running dual algorithm. It is enhanced the distance vector routing protocol. You don't need to maintain the entire topological database, but convergence will be very fast and all. I can like we can offer you equal cost multipath, unequal cost multipath, equal cost load balancing, unequal cost load balancing. Just like the link state routing protocol, we also are going to form the neighborship first, and then we will exchange the routes and everything. So they borrowed a few properties from the link state routing protocol. They implemented those in vector routing protocol, and they created a new protocol, new category of protocol called enhanced distance vector routing protocols. Enhanced distance vector routing protocol, they use enhanced distance vector algorithm called dual, diffusing update algorithm. EIGRP is the only protocol that comes under this category. It was a proprietary protocol up to 2013. In 2013, it was released as an open standard protocol by Cisco. Some people say that their documentation got leaked somewhere in China. Some people say that they wanted to like everyone to use EIGRP. There are a lot of reasons that people say why they released this as an open standard. The main reason that people believe was their coding was leaked actually online. So they thought that since our coding got leaked, so everyone will now be able to implement it, or maybe they will create some protocol be inspired from the same. So they said like, okay, let's release it as an open standard. But who knows like what is the truth? But this is what people believe. So dual diffusing update algorithm, it offers rapid convergence time for changes in the network topology. Like you said, someone said that EIGRP is actually, in terms of convergence, EIGRP is the fastest protocol you will see ever. Means like, I'm not saying that OSPF is very slow, but if you compare OSPF and EIGRP is way faster than OSPF. So it offers rapid convergence time for changes in the network topology. Updates are only sent when there is a change in the network. Unlike distance vector routing protocol, where in every certain time interval, the update messages are sent. In EIGRP, updates are only sent when there is a change in the network. It does not send full routing update. It only sends whatever has changed. It is only going to send whatever has changed. As the distance vector routing protocol, they send entire routing table in every, for example, 30 seconds or 90 seconds. But this enhanced distance vector routing protocol, they don't do that. They send the information only when something has changed, and only whatever has changed that will be propagated to the neighbor device. Just like the link state routing protocol, routers, EIGRP will also perform neighbor relationship with the help of a message called hello message. Same hello message was being used in OSPF as well. Same name for the message they have used here as well. It can perform equal and unequal both the type of load balancing. It can consider not only bandwidth, but it can also consider delay, reliability, load, and MTU to decide which path is the best path to go to the destination. So the metric in EIGRP is calculated using the metric calculation formula, and that metric calculation formula is going to use bandwidth, delay, reliability, load, and MTU. By default, bandwidth and delay only. So using the bandwidth and delay, what is the bandwidth? What is the delay? Bandwidth, delay, bandwidth, delay, bandwidth, delay. What is the bandwidth and delay? So based on the bandwidth and delay, the router will calculate the metric value to reach out to a destination, and whichever path has the lowest metric will be selected as the best path, either this one or this one or this one. The best path selection is not done based on hop count. So the best path selection is done based on bandwidth, load, delay, reliability, MTU, based on the metric calculation formula, but not only on the single factor. So it has multiple metric components. EIGRP can consider multiple components for metric calculation, such as bandwidth, load, delay, reliability, and MTU. Based on that, it will calculate one metric value, and based on that metric, it will decide which path is the best path. So EIGRP is actually better. If you talk about EIGRP is actually better in terms of convergence and everything. And but the only problem with EIGRP is that it was a proprietary protocol. So if you have to use EIGRP, you have to purchase a Cisco device. It could have been a marketing strategy for Cisco as well, that I will give you all these facility, unequal cost, load balancing, successor, feasible successor, all that thing, but you have to purchase a Cisco device for the same. So one algorithm that protocols can use is the distance vector algorithm. Second algorithm that they can use the link state algorithm. The third algorithm that they can use is enhanced distance vector algorithm. And the final algorithm that the protocols can use is called path vector algorithm, which is quite similar to distance vector routing protocol algorithm. Like distance vector routing protocol, they use a distance vector algorithm. Similar to that, we have a protocol called BGP, and that BGP protocol is going to use this path vector algorithm to decide the best path. Now, why we call that path vector algorithm? Because in BGP, whenever a network is advertised to the neighbor router, the AS path information is sent along with that. So when this router 2 receives this subnet information, router 2 can see that this subnet belongs to AS1. When this router 2 passes that information to router 4, it will add its own autonomous system information in a list fashion into the existing autonomous system list. So router 2 says that if you have to go to that destination, my autonomous system number is 2 and the neighbor autonomous system is 1. So that AS path information is listed in a list format like that. When the neighbor router receives it, it will come to know that if it has to go to that destination, it has to cross 2 autonomous systems, 2 and 1. When it advertises that information to the neighbor router, it will add its own autonomous system in that list. When this router advertises the same information to the neighbor router, it will add its own autonomous system in the list. Point is, every router in protocols such as BGP has a clear idea how many number of ASs it has to cross to reach out to that particular destination. This router 4 is also getting the same information from here. Router 4 knows that if it has to go to that destination via this path, 2 ASs it has to cross. It also knows that if it has to go to that destination via this path, then also 2 autonomous systems it has to cross. So now router BGP will decide the best path based on how many number of ASs it has to cross. It is one of the criteria in multiple criterias. AS path is one of the criteria based on which BGP decides its best path, and that is why we call that path vector routing protocol. We call that path vector routing protocol because BGP uses AS path attribute to decide the best path to reach out to the destination. Let's say if I have to go to that destination via this path and total number of ASs that we have to cross is 3. If I have to go to this path via this, if I have to go to that destination via this path, and let's say that the total number of ASs that we have to cross is 2, it will choose this over this. So a path vector routing protocol decides the best path based on how many number of ASs you have to cross from one particular path. And that AS path, because of that, this protocol is called path vector routing protocol. This AS path list also helps in loop avoidance. Why? Because if you receive a subnet information and that AS path list contains your own autonomous system number, you will understand that either the prefix has been generated or advertised from your own AS, or it has already passed your autonomous system. So for example, router 3 advertises that subnet to router number 2. Router number 2 receives it. Router number 2 checks the AS path list of that subnet and it finds its own AS number in that AS path list. It will immediately understand that this prefix has already crossed the autonomous system, so I don't have to accept it, otherwise it will cause the loop. So AS path list also acts as a loop avoidance mechanism in the path vector routing protocols. A path vector routing protocol guarantee a loop-free path by keeping a record of each autonomous system that a routing advertisement traverses. Anytime a router receives an advertisement in which it already sees its own autonomous system, advertisement is rejected because accepting that will cause a routing loop. So AS path, we'll talk about that in more detail in BGP. AS path is one autonomous system information, is one of the criteria based on which the BGP decides the best path. And this AS path attribute is used in loop avoidance. It is used in best path selection. That's why we call this BGP protocol as path vector protocol, path vector routing protocol, because it uses path vector algorithm to decide the best path. So there are 4 algorithms based on which the routing protocols can decide which path or is the best path, which route they have to advertise, which they don't have to.